The following message is best viewed on an oscilloscope.
Okay, thank you everyone. Thank you for joining us. This is a Neutrino session 3, and today we will have 11 talks, and each talk will have 15 minutes, including question and answer time. So I think let's get started with the first talk. First, detection of solar neutrinos from CNO cycle with Brexino from Andonanic. Please.
Okay, good morning. Can you see my screen?
Yes, I can see your screen.
Okay, so
but not full screen yet.
It's in full screen now. So
okay.
I'm going to tell you about the first detection of solar neutrinos from CNO cycle in Brexino. So Brexino is a detector which consists of 280 tons of liquid scintillator viewed by 2212 8-inch PMTs inside an active water Cherenkov muon Vito. For this specific...
Sorry to interrupt, but we don't see your full screen and the screen is not changing.
Maybe there is a delay.
We can wait a few minutes, but I think anyone else confirm that you don't see the full screen?
No, yeah, we don't see the full screen and it's no delay.
This is not a full screen, and this is a full screen.
We see now black screen.
Black screen, huh?
Yes, black screen.
Yes, we see a black screen.
I stop and redo the sharing.
If not, I can also share for you.
So I redo the sharing.
You want to try it a second time? If not working, then I can share for you.
Yes, okay, thank you.
We can see now full screen.
Okay, so as I was saying, the Brexino consists of 280 tons of liquid scintillator inside an active water Cherenkov detector. For this specific data set, we have used 238 active channels and an energy resolution at 1 MeV of 6% and a spatial resolution of 11 centimeter at 1 MeV. So this is the inside of the Brexino detector, the inner detector with the photomultipliers, and this is the detector completely filled with liquid scintillator in 2007 when we started the data taking. So Brexino data taking has been divided in 3 phases. The first phase ended in 2010. Between the first and the second, we performed a liquid scintillator purification campaign by means of water extraction. And then at the end of phase 2, we installed a thermal insulation system and an active temperature control system, which is important for the present analysis of CNO neutrinos. In phase 3, we detected the CNO neutrinos. So solar neutrinos are produced, as you know, by the PP chain and by the CNO cycle. In particular, for the CNO cycle, neutrinos are produced by beta decay of nitrogen and oxygen, mainly, with a subdominant production of beta decay of fluor 17. So while this process is running, hydrogen is fused into helium. Solar neutrinos are related to energy production. As a matter of fact, as you can see in this relationship, the luminosity of the sun can be written in terms of solar neutrino fluxes when one assumes energy conservation. So the importance of the two-chain production for neutrinos depends on the mass of the star and, as a consequence, on the central temperature. For the sun in particular, where you have about 15 million Kelvin at the center of the star, the main production energy is due to the PP chain. CNO cycle is producing only about 1% of the energy. And this makes more difficult the detection of these neutrinos. So here you can see the solar neutrino spectrum, energy spectrum on the left. And on the right, when you fold this spectrum with the neutrino electron elastic scattering, as is the case in Borexino, then you can see the visible spectrum as a function of the electron recall energy. And in particular, what you can notice is that the CNO neutrino spectrum, which is in green here, is featureless. On the contrary, the beryllium-7 and PP neutrino spectrum has a peculiar Compton-like edge, which makes more easy the detection of these neutrinos because they are monoenergetic. So in this table, you can see the achievements on solar neutrinos by Borexino. So this column here reports the prediction of the standard solar model for high metallicity and low metallicity. And I report here also the rate, which is the measurement performed in Borexino, and the Borexino flux when you assume neutrino oscillations. So Borexino before 2020 has measured all the sources from the PP chain. And this year we have performed a measurement of the CNO neutrinos. So what is the challenge to measure CNO neutrinos? First of all, the expected rate is small. It's between 3 and 5 count per day in 100 tons from the solar standard model. The main background is bismuth 210, which comes from lead 210. And here you can see the decay chain of lead, which produces bismuth 210 and polonium 210, beta and alpha respectively. So if there is no other source, but only lead, the chain is in secular equilibrium and the activity of bismuth is the same as of polonium. The other important point is the strong correlation between CNO, PP, and bismuth. As you can see here, this is the real data, where I have highlighted in red the CNO expected spectrum, and in blue and red and green the bismuth and PP. So there is a strong correlation between these spectra, and therefore one needs to have an extra information to break this degeneracy. In any case, the expected signal to background ratio is between 0.2 and 0.3. So this makes the measurement more difficult. So let's go to this slide. So the strategy is based on the thermal insulation and temperature control. On this upper left plot, you can see a picture. You can see the water tank of Borexino with the thermal insulation. And inside underneath the thermal insulation at the top, there is also a temperature control system by means of which we can inject some heat. So on the plot on the left, on the right, you can see the deployment of temperature probes to measure the temperature in different locations inside the detector. And Borexino is sitting on a cold floor at 7.5 Celsius. And at the top, the temperature, the air temperature, it's about 15.8 Celsius. So there is a gradient of 0.5 Celsius per meter. And the idea is to keep this gradient stable in time in such a way that we avoid convection currents inside this scintillator. And in the lower left plot, you can see the trend of the temperature after the startup of the insulation and temperature control system. So this is very important for the CNO measurement. The strategy is based on mitigation of correlation due to bismuth-210 by reducing the convection currents and keeping the gradient constant. The convection currents can bring inside the fiducial volume bismuth, but mainly polonium-210. The second point in this strategy is to exploit pole shape discrimination to determine polonium, and from polonium determine bismuth, determine bismuth-210. So here you can see the trend in time of polonium-210 measured by means of the pole shape discrimination inside the fiducial volume. As you can see, before the thermal insulation installation, the polonium was moving a lot inside the fiducial volume. And even at the center of the detector, we had many counts per day. After the installation of the thermal insulation and the temperature control system, convection currents diminished a lot, decreased, and at the center of the detector, we have a very low polonium rate. As a matter of fact, we can establish that the polonium rate is due to the bismuth rate, which is in secular equilibrium with polonium due to intrinsic lead-210 contamination, plus polonium coming from the vessel, from the outer region. And this is taken inside the fiducial volume by means of the convection currents. So if the convection currents are zero, then the polonium and the bismuth activity is the same due to the secular equilibrium. So the real idea is that to measure polonium inside the fiducial volume where there is no convection currents and determine a constraint for the bismuth. The other important point, once the bismuth rate is measured, is to establish that the bismuth-210 is uniform and in time and in space. So stable in time and uniform in space inside the fiducial volume. And we have tested that. And here you can see in this plot the trend of beta-like events in the region of interest, where there is no polonium activity. And in this region, you can see that the beta event rate is stable in time. And we have also tested that it's uniform in time. And this is because the distribution of lead-210 inside the liquid scintillator is uniform. So with this information, we determine an upper limit for the bismuth-210 rate of 11.5 plus minus 1.3 count per day in 100 tons, including systematic effects. So with this, we can proceed to analyze the data and determine the CNO solar neutrino flux. So we have chosen an energy window for the spectral fit between about 300 keV and 2.6 MeV. We have fit at simultaneously the energy spectrum and the radial distribution of the events. The free parameters in the fit that you can see here on the upper right plot is CNO, krypton, carbon 11, which is cosmogenic, potassium 40, thallium 208, bismuth 214 from radon, and beryllium 7 from solar neutrinos. The solar neutrino PP rate is constrained to 2.7 from the PP measurement, and the bismuth 210 is constrained to what we have established using polonium 210. So we have used 1,072 days of lifetime and standard selection cuts, so reducing muon and muon daughter, selecting the fiducial volume and exploiting a threefold coincidence to reduce the carbon 11 cosmogenic background. So here you can see in the lower right plot the delta chi-square profile as a function of the CNO rate. The solid black line is without systematic, is with systematic, and the dotted line is without systematic. In addition, the histogram reports a counting analysis just considering a beam of energy, which is the one highlighted in the upper right plot in yellow, where the main component is, as a matter of fact, CNO neutrinos. So from this, we have determined this result here, which is the first measurement of CNO neutrinos. So the updated table, which I've shown before, is this, with all the solar neutrino measurements in Borexino, and this is my conclusions. So the observation of CNO, it's a breakthrough in solar neutrino science, and I'm open for any questions from you. Thank you for your attention.
Thank you very much. And if you have a question, I think we have like a short question. If you have a question, please raise your hand. Okay, I think we have one, and let me see. So please, let me see who is, but I cannot see. I think we have one audience raise the hand, but I don't see who this is.
Hello, this is Tony. Yes.
Yes, please, go ahead.
Okay, so excellent talk and congratulations again for the CNO neutrino observations with the 5 sigma. As far as I understand, your result is, uncertainty on your observation is dominated by statistical uncertainty. And my question is, are you going to take more data until you, disinstall your detector, or you stop? You already stopped, or what? How is it? What's the situation?
Okay, thank you for your question. No, we are taking data. As a matter of fact, at the end of last year, we have improved the temperature control inside the experimental hall. And so now we have a very accurate determination of the air temperature inlet inside the hall. And this is improving the stability of the inner part of the detector. So we hope that with the data that we are taking now before the decommissioning of the detector, we could even improve this measurement, because we could improve the determination of bismuth 210. So presently we're taking data, and we think there are some uncertainty, but we can take data till the end of this year and before the decommissioning. But the decommissioning time is unknown at the present time, and so we are going to take data till we can keep the detector running. And we hope we can, with this improvement we made last year, we can even improve a little bit the present result.
Thank you.
Thank you. I think we are running out of time. So let's go. Let's thank our speaker, and let's go to second talk, the reactor anti-neutrino flux and spectral measurement at Daya Bay. Feng Peng, would you please share your screen? Okay, please.
going to talk about the reactor anti-neutrino flux and spectrum measurement at IB. I'm from East China University of Science and Technology. Here is a brief overview of the IB reactor neutrino experiment. It is designed to measure T213 using antineutrinos produced by 6 reactors, and each reactor with 2.9 power. We installed 8 identically designed anti-neutrino detectors in the experimental halls, 2 near halls and 1 far hall. And this experiment starts from Christmas of 2011, and we discovered the non-zero T213 mixing angle in 2012. And the IB collaboration is an international collaboration. Now we have 191 collaborators in 41 institutes from Asia, Europe, and North America. Reactors are very strong anti-neutrino sources. And in the IB, the 6 reactors have a total thermal power of 70.4 gigawatts, producing 3.5 times 10 to the 21 electron antineutrinos per second. And the antineutrinos are mainly produced by the beta decay of the fission fragments of these isotopes to uranium and to plutonium. And the fission fragments of the isotopes has intrinsic mass distribution. So for each isotope, they have a intrinsic antineutrino spectrum, like shown here. This is a Hilbert-Muller model showing the antineutrino spectrum of the 4 isotopes. In the IB, we detect antineutrino with inverse beta decay and using liquid scintillator detector. This detector is designed with 3 zones. The inner zone is filled with 20-ton gadolinium-doped liquid scintillator at the antineutrino target. The middle layer is filled with liquid scintillator, 20-ton, as a gamma catcher. And the outer layer is filled with 40-ton mineral oil as a radiation shielding. And 192 PMTs are installed to collect the photon signals. The combined detection of the detector efficiency is 8.2%, plus minus 1.2% uncertainty, and the energy resolution is 8.5%. The neutrino interact with the proton via inverse beta decay, producing 1 positron and 1 neutron. And the positron annihilate immediately and producing a prompt signal. And the proton will be captured on proton or gadolinium later, forming a delay signal. So with this character, we can exclude the background effectively. The lower plot shows the inverse beta decay cross-section, and the dotted plot is the predicted antineutrino spectra in the detector. Besides the C213 measurements, the IB also did a series of antineutrino flux and spectrum measurement from the beginning, from 217 days data taking time to now 1958 days data taking. And the statistics now is 3.5 million IBs in the near site, which is 10 more than the beginning ones. And in this talk, I will talk about the recent work we did, the improved measurement of the reactor antineutrino flux and the IB, and the extraction of the 2 isotope antineutrino spectrum and the IB. In recent development, we improved our systematic uncertainties. The first one, we improved the energy scale uncertainty from 1% to 0.5%. And we reduced the lithium-9, helium-8 background uncertainty from 45% to 30%. And we reduced the spent nuclear fuel uncertainty from 100% to 30%. And lastly, we improved the neutron detection efficiency uncertainty from 1.69% to 0.74%. In the next page, I will talk about this. And to improve the neutron detection efficiency, we did a comprehensive detector calibration and model studies. For the calibrations, we used 3 calibration axes vertically inside and outside the gadolinium region with 2 neutron sources, and a total 59 source calibration points are obtained. And for the models, we use 3 neutron scatter models and 4 neutron gadolinium capture gamma models. And combined altogether is 20 simulated model combinations. With these calibrations and model studies, we improve our neutron detection efficiency uncertainty from 1.69% to 0.74%. And the total flux uncertainty improved from 2.1% to 1.5%. So here is the recent anti-neutrino flux measurement using 12 or 30 days data. And we compared our measurements to the Mueller prediction. In the previous analysis with 621 days analysis, the ratio is 0.946 plus minus 0.02. And now this is the ratio is 0.952 and with an improved uncertainty 0.014. And this result agrees with the other experiments. In this left plot, the blue line is the world average, and our result agrees with the average within 1 sigma range. And this is the reactor antineutrino spectrum measurements with 1958 days measurements. You can see, comparing with the previous analysis, the uncertainty improved a lot. And the comparison with the Mueller model, the spectral shape disagrees with the Mueller model at 5.3 sigma. And an excess in 4 to 6 MeV range is observed with 6.2 sigma discrepancy. With much more events collected, we begin thinking of extract the isotope spectrum from this total measured spectrum with the detector data and the fission fraction data provided by the nuclear power plant. Here is an example of fission fraction in a typical refueling cycle. You can see the fission fraction evolves with the burn-up. And you can expect that the total antineutrino spectrum will evolve with these changes. This plot shows all the refueling cycles stacking together from the beginning of our experiment. And we also defined a quantity called the effective fission fraction, which is a fission fraction observed by detectors because each detector can observe 6 reactors and with different baseline. And these reactors are at very different burning stages, and each detector has some differences. So we defined this fission fraction, effective fission fraction. And here shows the effective fission fraction of plutonium-239 of near sites. You can see these up and downs reflect the activities of the reactors. And the effective fission fraction of uranium-235 ranges from 50% to 65%, and for plutonium ranges from 24% to 35%. Here is how we extract the spectra of 2 isotopes with 1958 days data. Firstly, the 3.5 million antineutrinos detected in near sites are divided into 20 groups ordered by the plutonium-239 effective fission fraction. Then we fit the uranium and the plutonium spectra as 2 unknown arrays with 26 energy beams for each isotope. Here's the chi-square function we constructed. And this term is the likelihood function comparing the predicted spectrum of the 20 groups and the measured spectrum of the 20 groups. And plus 1 constraint on nuisance parameters. Since our measurements are not sensitive to uranium-238 and plutonium-241, so we use them as constraint terms in this term. And using Mueller model as their priors and assign a large uncertainty, more than 10%, both in rate and shape. We also consider the time-dependent contributions from non-equilibrium isotopes, then nuclear fuels, non-linear nucleus, and backgrounds. And we also did an independent analysis using Markov chain Monte Carlo based on Bayesian inference on and obtains consistent results. And here is the extracted the uranium-235 and plutonium-239 spectra, together shown with the Hume model. And this is the first extraction of the 2 isotope spectrum of commercial reactors. And in the 4 to 6 MeV range, the 2 isotope spectra have similar bond structure like the total spectrum. And the local deviation for uranium-235 is 4 sigma. For plutonium-239 is 1.2 sigma due to large uncertainties. And for the IBD ratio, uranium-235 is 0.92, plutonium-239 is 0.99. So you can see that uranium-235 is more likely to be responsible for the reactor antineutrino anomaly. In previous slide, we treat uranium-238 and plutonium-241 as constrained term. So you can see that they have some, this fit has some dependence of the 2 terms. So to reduce the plutonium uncertainty, we combine the plutonium-239, plutonium-241 as 1 term using this formula by fitting the relations with the fitting fraction of the 2 plutonium isotopes. And after this combination, we extracted the uranium-235 spectrum and plutonium combo spectrum. Then the dependence of the input of plutonium-241 is largely removed. So the extracted plutonium combo spectrum uncertainty is 6%, which is much smaller than 9% for plutonium-239 only fit, shown here. So here's my summary. In recent development, we reduced particular cinematic uncertainty and acquire more than 50% more statistics than the previous analysis. And we improved measurements of reactor and neutrino flux and agreed with other experiments. And we improved the measurements of reactor neutrino spectrum. The spectral shape disagreed with the Hume model prediction now is at 5.3 sigma. And the bump range, the local deviation is about 6.3 sigma. And we have a first extraction of the 2 isotope spectrum of commercial reactors. And both of them have similar access in the bump range. And uranium-235 is more likely to be responsible for the reactor antineutrino anomaly. And this extracted spectrum can be used as a reference spectrum for other experiments. That's all. Thanks. Questions?
Thank you. Thank you. We have time for a couple questions. So please raise your hand if you do have one. Okay, so I don't see any question. Since we are kind of delayed, so I think let me just let's just start with the next talk. If you have some questions for Fengpeng, you can ask him offline. So let's go to the 3rd talk. Latest result, neutrino oscillation results from the diabetic experiment from Beta Reskovic. Beta, please.
Okay. Yeah. Hi. Okay. I'm following on Fengpeng. I will also talk about the experiment, but I will cover the latest reactor neutrino oscillations. Okay, so as there will be a lot of introduction comment to Fengpeng. So as Fengpeng already introduced, the Abbey experiment is located about 60 kilometers from Hong Kong at the coast of southern China, and it was primarily designed to measure θ1-3 mixing angle through the reactor antineutrino oscillations and about the baseline of 2 kilometers. And it is very successful experiment because it's actually discovered this non-zero value of θ1-3 just after a few months of running. The Darby experiment uses 6 reactors as a source of these reactor antineutrinos, and the reactors in general, not only Darby reactors, are the source of pure electron antineutrinos. It's very good, there are no contamination. And it's also very, very strong source because each of Darby detectors produce about 6 to 20 antineutrinos per second isotopically emitted, to all directions. Okay, these antineutrinos are detected in 8 functionally identical antineutrino detectors placed in 3 underground experimental halls. So while Feng results were about this near hole detectors, which are adjacent to the reactors, my result will, the results I'm going to report will be mainly based on the fire detectors. There are 4 antineutrino detectors based about this ideal baseline of about 2 kilometers, where we see the effect of the neutrino oscillations. In each experimental hall, these detectors are submerged in the water pool, which is instrumented for muon detection, the Cherenkov light caused by the muons for the background suppression. So each of our detectors, as Pamela already explained, consists of three nested volumes, where 2 inner volumes are filled with liquid scintillator. The most inner one even is doped with a gadolinium, and it works as our main target. We detect our antineutrinos through this inverse beta decay reaction, which was already described, where the antineutron hits a proton and produces the positron and neutron, where the positron quickly loses its energy and annihilates with the electron, and the energy of the prompt signal can be directly linked to the energy of incoming antineutrino. For the neutron, it takes some time till it gets thermalized, and eventually it gets captured on atom of gadolinium, producing this 8 MeV gamma cascade. And since it takes some time, it is a delayed signal. The neutron can also capture on hydrogen, emitting just 2.2 MeV gamma. And then these prompt and delay signals are spatially and time correlated, which really helps us to suppress the background of any kind beyond any belief. I mean, it's very strong suppression. Darby is actually low background experiment with only 2% of background to Sigrid ratio for this neutron capture on gadolinium in all the detectors. So since I'm the first to speak about neutrino oscillations in this session, let me give you some brief introduction. So currently, it's well established that flavor states, neutrino flavor states, when we've got currently, we think that they are 3 flavor states, they are a superposition of mass states, and this superposition can be parameterized through this mixing matrix, which features 3 mixing angles and 1 delta CP variation phase. And each of these sectors can be actually explored by neutrinos from different sources at different energies. And we focus on this middle block, which features θ13, which was last to known mixing angle discovered by the Darby, because it can be studied with the reactor neutrino oscillations at the baseline of 2 kilometers. And apart from that, neutrino oscillation frequency is driven by the mass square differences, the differences between the masses of these mass states here. They are called mass states. Okay, so how do we actually measure these oscillation parameters? So what in reactor antineutrino experiments, we are looking at the survival probability of electron antineutrinos, where at the reactor, I already told it's pure source of electron antineutrinos, so there is 100% of electron antineutrinos, okay? And then, however, if we put our detector at some distance, and also it's a function of energy, we do not see 100%, we might see some deficit. And this deficit is because of some of the neutrinos can oscillate to other flavors. And these oscillations can be expressed by the survival probability, which has got kind of 2 modes. One I would call medium baseline, which for reactor antineutrinos is demonstrated at the oscillation length of about 60 kilometers, which was first discovered by the Cambland experiment. And we've got this also short baseline oscillation mode, which features this θ13 mixing angle, and it was discovered by Darby experiment. So let's just zoom in this 2 kilometer distance where I plot the oscillation formula. The medium baseline term does not matter. It's only about the short baseline term, And then we can see that, if the deficit observed at about 2 kilometers is proportional to the amplitude of the oscillation, which is driven by sine squared theta 1,3. And also if we measure the position of this minimum, which is determined by the oscillation frequency, which is driven by the mass square difference, we can also determine this difference between masses of the neutrinos. Okay, it sounds like very easy, right? But there is a reason why theta 1,3 was the last known mixed angle, because it's very tiny. So we really need to optimize our experiment to be very sensitive. And what Darby did, and not only Darby, but also other experiments measured theta 1,3, we employ these near and far detectors, where the near detectors kind of measure the flux of antineutrinos and also the spectrum directly, without almost any oscillation effects, because there is, with the prediction of reactor antineutrinos, there is large uncertainty related. So we can measure it more precisely. And then we also have this fire detector, which sits at the ideal baseline. This is also optimized for Darby, where we sit at the oscillation maximum or minimum. I mean, it depends how you look at it. Essentially, we see the maximal effect of the oscillations, and then we just compare the deficit of the seen in the fire detector compared to the near detector. And apart from that, Darby has got powerful source of reactor antineutrinos, sits next to one of the most powerful reactor complexes in the world. We've got a lot of large detectors, and also we are a background experiment. So, as I already told, Darby experiment already discovered theta 1,3 in 2012, but we are still keep improving our measurement. And apart from adding statistics, we also improve our systematics. And essentially, my list is the same as list of Fanpang. We were able to actually halven our absolute energy scale uncertainty, having this special calibration campaign, and also employing the full ADC readout in one of our ADs. We were also able to reduce our dominant background, which is from the decays of the cosmogenic isotopes like lithium-9 and helium-8. And on the reactor part, we were able to actually significantly reduce the spent reactor nuclear fuel uncertainty, or because there are neutrinos coming from the spent nuclear fuel, by utilizing precise history of the spent nuclear fuel provided by the power plant. And with that, let's get to the results. So our latest measurement with the sample where the neutron got captured on gadolinium, it is based on almost 2,000 days of data, and it contains almost 4 million of antineutrino interaction, which is the largest reactor antineutrino data set in the world. So Darby is really powerful in this regard. And then what we can see, so this is the measured spectrum in the fire detector, where the red curve is the prediction based on the near detector measurement. However, we don't observe the red curve, we observe some deficit, which are the black points, the data, and then the best fit is the blue curve. And the best fit is very consistent with neutrino hypothesis. So if we translate it into this probability oscillation curve, we nicely measure this oscillation probability, so we can determine theta 1,3 and the mass square difference. And that's what we did. So with our value of sine squared theta 1,3, it has got world-leading precision of 3.4%, and the mass square difference we report in effective mass square difference. However, it can be easily translated to delta n squared 3.2 given some mass ordering. With the 2.8%, we actually have got a comparable precision with accelerator experiments, which also measure this parameter. And we are about still statistics dominated, so we will improve our result. And how? I mean, how? It's shown on this slide. So actually, Darby will end data taking at the end of this year, in December this year. And then what we expect with a final precision of sine squared theta 1,3, it actually be below 3%, and we reach almost 2% with the mass square difference. So that's very, very impressive. Apart from the study of the data sample where neutron capture on gadolinium, we also look at on the sample where neutron capture on hydrogen. And this is essentially independent analysis from oscillation analysis from GD sample, because the statistics are completely different. And it's mostly decoupled in systematics. However, this analysis with the neutron capture hydrogen data sample poses some challenges, because there is much larger background, like especially in lower energies. but also in general, the systematics are larger. So our latest result is actually quite old with only 600 days of data. And we got consistent result in θ13 from and GD analysis. And the update is under intense preparation. And I suggest to see the poster of Jingjing later today. Okay, and Diabay also does not just study the oscillation in 3 neutrino framework. We also go beyond and search for light sterile neutrinos. I mean, the sterile neutrino would be like additional flavor state apart from those 3 knowns, and then it is linked to additional mass state, and then additional mass square difference. And if such a state exists and there is a link between the sterile and active sector, we would see additional oscillation modes on the top of the known ones in general in our experiment. So our latest analysis based on 1200 days of data did not see any significant signal for the sterile neutrino oscillations. And thus we were able to place the most stringent limit on this kind of new mixing angle for the new mass square difference below 0.2. So this is essentially in this parameter space, we include everything here. And then we further extended our exclusion limits combining with Bouguer experiments. So at this larger delta square values, we were also able to exclude this. Okay, so we did not combine only with Bouguer 3 experiment, we also combined with MINOS and MINOS plus experiments. And we did it in order to scrutinize some like allowed region for sterile neutrino oscillations from the observation of electron neutrino excess in the muon neutrino beam and LSND and mini-boon experiments. So why do we actually combine with MINOS and MINOS plus? Because the thing is following. In these experiments, LSND in mini-boon, the oscillation or the probability can be, I mean, the excess of electron neutrinos they observe can be, could be interpreted as a sterile neutrino oscillation with this new mass square difference and this effective mixing angle. And this effective mixing angle actually consists of θ14 and θ24. And then here comes the combination, okay? So θ14 is constrained by Diabay in this disappearance channel of electron antineutrinos, while θ24 is constrained by MINOS and MINOS plus in this disappearance channel of neutrinos and antineutrinos. And then combining together, we can actually constrain this effective mixing angle, and then we did. And then essentially what we got, we did not see also any signal of sterile neutrino oscillation, and we were able to exclude the allowed parameters, sterile neutrino oscillation parameters for LSND and mini-boon on more than, for delta square for one smaller than 1.6 EV squared, everything from down here, on 99% confidence level. And we were also able to rule out the global fits just on appearance experiments and also the global fit of all the oscillation experiments and global fit of sterile neutrinos, again, on more than 99% confidence level. And if you want to know more, I suggest about this sterile neutrino searches, please see the poster of Georgian again later this afternoon, or I mean, maybe it's still in the morning for any other time. So this brings me into conclusions. So yeah, the latest Diabay reactor antineutrino oscillation measurement is based on where we use the sample with where the neutron capture on gadolinium with more than 5 years of data yielded the most precise measured value of θ13 in the world, and the mass square difference delta m square EE comparable with a comparable precision to accelerator experiments. We also have independent analysis, independent θ13 measurement using the sample of neutron capture on hydrogen. And it's quite old and new results under preparation. We also search for light sterile neutrinos and there is not found any. And so then the Diabay, Bouguer 3, MINOS plus themselves or even together placed very strong limits on sterile neutrino mixing. So, and just to conclude, I already mentioned the Diabay will end data taking in December this year, and then the final result on θ13, the final value will be probably the standard for this, for this mixing angle for the foreseeable future. Okay, so stay tuned.
Thank you, Beda, for this nice talk. And I think we are running out of time for your questions. So I encourage everyone who have questions to go to the Mattermost neutrino physics channel for any other questions not being able to raise here. Now we go to next talk, a recent result from Reno, from Xin Changdong.
Okay, can you see my screen?
Yes, please go ahead.
Okay, I'm Changdong Shin from Cheonnam National University, Korea. Today, I will talk about the recent result from LUNO. The LUNO collaboration consists of 9 institutions and 40 physicists, and this experiment site is Hanbin Nuclear Power Plant at Yangon. We started data taking from August 2011. This page shows the LUNO experimental setup. In Hanbin Nuclear Power Plant, there are 6 reactors. The total thermal power is about 16 kilowatt. We installed 2 identical detectors on the mountain. Near detector is located at around 300 meters from reactor array, and the part detector is 1.4 kilometers. The overburden is 120 meter water equivalent and 450 meter water equivalent, and near and part detector respectively. And we are using identical detector, therefore we can cancel out the systematic uncertainty related with the reactors. The LUNO detector consists of 4 concentric cylindrical detectors from center to outer: target, gamma catcher, buffer, and beetle region. Target is filled with 16 tons of gadolinium-loaded liquid scintillator, and the gamma catcher is filled with liquid scintillator. The buffer and the beetle region are filled with non-scintillation oil and pure water, respectively. And 354 PMTs are mounted on the inner wall of the buffer, and 67 PMTs are mounted on the inner wall of beetle. We use the inverse beta decay process to detect the neutrinos. Electron antineutrino from reactor occurs the IVD reaction in the detector, and the IVD reaction requires a threshold energy of 1.8 MeV. After IVD reaction, it makes positron and neutron. Then positron makes signals through pair annihilation, and is called a prompt signal. The energy range of this prompt signal is 1 to 8 MeV. After that, neutrons are captured on gadolinium or hydrogen, and this is called delayed signal. The NGD case has 8 MeV energy and a mean catch-up time of 30 microseconds. This case is used for our main analysis. In the NH case, the energy is about 2.2 MeV, and the mean catch-up time is about 200 microseconds. This page summarizes the recent result from LUNO. We published the paper about pure composition-dependent reactor antineutrino yield at LUNO, and observation of reactor antineutrino disappearance using delayed neutron capture on hydrogen at LUNO in 2019 and 2020, respectively. And we also reported about search for sub-electron sterile neutrino at LUNO. This is posted at arXiv in this year. In addition, we updated the analysis result using 2,900 days of data. This page shows the measured spectrum of IVD prompt signal. This result uses the 2,900 days of data. Black dot is the observed IVD candidate. Blue line is expected IVD spectrum. The number of observed IVD events is about 1 million in near detector. The PAR detector has 100,000 events. The background fraction is 2.3% and 4.8% at near and PAR detector, respectively. And this result shows clear access at 5 MeV. This plot shows observed and expected daily IVD rate. A low line is expected rate with oscillation using best fit value of oscillation parameters. The variation of IVD rate is effect from reactor on and off. The observed and expected rate are in good agreement. We also check the correlation of pipe MV excess with the reactor thermal power. The x-axis is the IV delay from the thermal power, and the y-axis is the pipe MV excess rate. And the bottom plot shows the fraction of pipe MV excess over each point. This fraction is about 2.5% at both near and far detector. This plot indicates that pipe MV excess has a clear correlation with the reactor thermal power. This means that pipe MV excess comes from the reactors. We also measure the absolute reactor neutrino flux. The data for prediction was determined to be 0.940 using data of the near detector. Most other experiments also show that the measurement results are lower than the prediction. And this deficit indicates an overestimated flux or possible oscillation to sterile neutrinos. Here is a part 2 near prompt spectrum. Blue line is the expected spectrum with no oscillation. Yellow line is the oscillation case. Both spectrum based on observed spectrum in near detector. Black dot is the observed data at far detector. In the bottom panel, this shows the data to prediction curve. You can see the obvious oscillation spectrum. And we updated the sine scale to theta 1,3 and the delta ME scale using 2,900 days of data. Black cross marker is the result of late early analysis. It is used to delta ME scale of PDG. And the black dot is the best fit value with the late plus spectral analysis. The sine scale to theta 1,3 is measured to be 0.089. The statistical and systematic uncertainty is about 0.004. Delta ME scale is 2.74 10 to the minus 3 powered electron volt scale. Statistical uncertainty is about 0.10 and the systematic uncertainty is about 0.06. As shown in this plot, there are global average value of oscillation parameters. The Lunos result about sine scale to theta 1,3 is consistent with the global average. And there is NH result. This result is also consistent with the other result. I'm going to talk about this NH result in a moment. However, the result of delta 32 scale is slightly larger than global average in both normal and inverted hierarchy. It can also show the survival probability as a function of effective L over E. The blue line is a prediction curve obtained from near data with the best fit value of oscillation parameters. The black dot is the data of far detector. These data will describe the prediction curve. We are also analyzing using NH event. The motivation of NH analysis is independent measurement of theta 1,3 value and the consistency and the systematic check on reactor neutrinos. This analysis is difficult to remove background due to long catch-up time and low energy of delayed signal. However, it is able to use event of gamma catcher, which is twice than target volume. Therefore, the statistics of NH event is enough for the analysis. We reduce background fraction via code optimization, and we obtained the result of late early analysis result. As shown in this page, there is a measured spectrum of prompt signal using 1,500 days of data. Even though we tried to reduce background fraction, a lot of accidental background are remained in the final sample compared to NGD sample. As shown in this figure, NH result also show the 5 MeV excess. This fraction is also about 2.5% at both near and far detector. And the sine scale to theta 1,3 is obtained to be 0.086. Statistical uncertainty is 0.008. Systematic uncertainty is 0.014. This result is consistent with the NGD result. The sterile neutrino search result is as shown in this page. For this analysis, we used 2,200 days of data with the NGD event. This analysis used the spectral sake comparison between near and far detector. On the left side, this plot shows the observed prompt energy spectrum divided by expected spectrum with the best peak value of 3 neutrinos. The gray band is represent to total uncertainty of 3 neutrino model. Other solid line is assumed the 4 neutrino model using 3 different parameters of delta M square. In the right side, this plot shows the comparison of exclusion limit from other experiments. The black solid line is Luno's result with 95% confidence level. The right side region of black solid line is ruled out. Since each experiment uses different confidence level, we cannot compare the result accurately. However, Luno's result rule out little more region at low delta M square level. This is a summary. We update the value of zeta 13 and delta ME square using 2,900 days of data. And the absolute reactor neutrino flux is obtained to be 94%. And we also measured zeta 13 value using NH data. And we reported the post-Luno sterile neutrino search result. Okay, thank you very much.
Thank you for this nice talk. And so question time. Please raise your hand if you have a question.
Hi, Chen. I have a question, but I cannot raise my hand.
Well, just go ahead. You can speak.
Yeah. So, okay, yeah. Thank you for a very interesting talk and a lot of results from Reno recently. I have a question. First, on slide 8, you showed the number of antineutrinos over time. And I with this last 700 days of data, it seems that the power plant is running in half power or something like. Can you comment on that? Do you know if they are like refurbishing some of the reactors, or how come, you know, they are running on the very low power?
Please tell me again.
Yeah, I mean, in this last 700 days, the average rate is about 200 IBDs, while the average rate before in this the first period of 2200 days, it's, let's say 500, or I don't know what is the average. So it seems that in the last 700 days, the power plant is running all the course. I mean, in general, in half of the power. Do you know why? Is there something going on in the power plant, like some construction?
There are in Hanbi nuclear power plant, there are 6 reactors, and sometimes only 1 reactor is going on. So
I see. Okay, yeah, but okay. And then I have a second question, if I may. So on slide 17, you showed the sterile neutrino limits, and then you showed that you are more sensitive than diabase for low delta the mass square differences. But when you showed the 3 neutrino result, your precision on delta M square is like, I don't know, at least 50% worse than diabase. I mean, can you comment on that? How you can achieve such a precision here, but do not see it in 3 neutrino analysis? I think they would be very linked, like that. It's hard to believe that with video optimization and shorter baseline, that you can actually achieve larger, you know, more stringent constraints than diabase for this region.
Okay. In order to understand about we should discuss with the diabase collaboration. However, we are thinking lower delta M square region is more sensitive in higher L/E value. So this is maybe correlated with the low energy data. And the method to calculate the chi-square is slightly different with the diabase. So we should discuss about this.
Okay, yeah, thanks for the answers.
Thank you. I think our time is running out. So if you have more questions, please go to the Mattermost channel. Thank you again. And let's go to the next talk. latest results of the stereo search for a stereo neutrino at a research reactor from Lawyer Labit.
Yes, can you hear me?
Yes, I can hear you.
Okay, I'm sharing my slide. Do you see it?
Not yet. I didn't see your slides. Okay, yes. Oh, hold on. It just disappeared again. Yes, I can see it. Please go ahead.
Okay, so I'm Loic, and I'm very happy to present you the latest result of the stereo experiment today. So the stereo experiment was designed to probe the oscillation toward the light sterile neutrino, which is one of the main hypotheses to explain the 6% deficit in measured flux, known as the reactor antineutrino anomaly. Another interesting measurement that can be done by stereo is the energy spectrum of a pure uranium-235 reactor to try to understand the spectral distortion that has been observed by several experiments, especially if it's due to an underestimation of some isotopes contribution. The detector is composed of a 2-tones gadolinium doped liquid scintillator target, which is segmented in 6 cells and surrounded by a gadolinium-free liquid scintillator gamma catcher. The whole detector is surmounted by a water Cherenkov muon veto, and we detect neutrinos through inverse beta decay, which gives a prompt signal, namely the positron ionization and annihilation, and a delay trigger, which is the neutron capture on gadolinium, which gives a cascade of gammas for about 8 MeV. Our main background is due to fast neutrons, which can mimic IBD signal. It's a surface level experiment located at Institut Langevin in France, near a compact research reactor core, which is fueled with highly enriched uranium-5. At a distance of about 10 meters, it is placed just underneath the water channel of the reactor, which provides additional shielding for about 15 meters water equivalent. We've been taking data now since November 2016, and you can see on the top plot, it's the cumulative days of reactor on data as a function of the time. Phase 1 and 2 amounts to 179 days of reactor on and 335 days of reactor off. The large number of reactor off days is critical to characterize our background. You can see in the bottom plot in red is the correlated pairs for the on and off periods. And so it gives you an idea of our signal to background ratio. We plan to continue data acquisition until the end of this year. The detector is calibrated each week with a manganese source and monthly with americium beryllium. And we use other gamma sources with energy that ranges between 0.5 and 4.4 MeV several times a year. You can see on the top plot the cosmogenic boron spectrum. And at the bottom of the plot is the data to Monte Carlo ratio, which shows a quite good agreement. On the bottom right plot, you can see the neutron capture on hydrogen, which we use to monitor the time stability of the detector. At the top is the relative deviation to the energy mean, and at the bottom of the plot is the energy resolution. And you can see that the mean energy is stable at the 0.3% level. And finally, at the bottom left plot, you can see the calibration coefficient normalized to the manganeses. At the bottom of the plot is the data to Monte Carlo ratio, which shows agreements better than 1%. How do we extract the neutrino signal? Well, we use pulse shape discrimination. So you can see on the top plot the time profile of light emission for an ionizing particle like a proton, you can see that the distribution will have a larger tail. So basically we compute the tail to the total charge ratio. And for an electronic recoil, we'll have a lower ratio than a proton recoil. Then we model our PSD distribution for the on data with 3 components. In red is the correlated background, which is shared with the off data, except that it is normalized with a parameter that accounts for the difference in the number of days between the on period and the off period. A second component in gray is the accidentals, and we account for the neutrinos with a Gaussian here in green. And both the on spectra and off spectra are fitted simultaneously. Once we have the neutrino signal extracted, we can perform the oscillation analysis. So it's a spectrum shape only analysis. We don't use information from the absolute traits. So basically we compare our data to our model, multiply by a parameter, which is different for each energy beam, but is common to all cells. That makes the analysis independent from the absolute traits and independent from the predicted spectrum. We take care of the uncertainties by adding nuisance parameters in the chi-square. The list of these uncertainties you can find here in this bottom table. The result of this oscillation analysis. So I must mention that we obtained our delta chi-square distribution from Monte Carlo pseudo experiments, because the standard chi-square law doesn't apply in our case. The contour you can see on the right is obtained from a 2-dimensional delta chi-square map. So you can see in red is the exclusion contour of our data, and at 95% confidence level. And in blue is the expected sensitivity with this number of days, 179 days of reactor on. Our data doesn't reject the no oscillation hypothesis, but we can exclude the error best fit point, which is the black star here, at more than 99.9 confidence level. The second result I wanted to present you today is the absolute trait measurement. So we obtained a ratio of observed to predicted rate of 0.948, which is in agreement with the current world average and consistent with the error deficits. You can find a lot more details on this analysis in the archive listed here. And the final result I will show you today is the unfolding of the spectrum shape. So to unfold, basically we compare our data to the unfolded spectrum multiplied by the response matrix. You can see here in this plot the uncertainty budget as the function of the prompt energy. And you can see that our main uncertainty is statistic. So we had a regularization term in the chi-square to smooth the unfolding of the statistical fluctuation. And we choose the strength of this regularization term to minimize the dependence to the prior spectrum, which has been chosen to be the U-bus spectrum for uranium-235. The result of the unfolding. So you can see here on the left is the result for the prompt energy, and on the right is the unfolded results. So on the top of the plot is the spectrum compared with the Uber model and the summation model. In the middle, you can see the ratio to the Uber model. So you can see here the spectral distortion. So a fit with a free Gaussian gives an amplitude of 10% at 4.8 MeV. And you can see at the bottom of the plot the local p-value, which gives the local measure of the local discrepancy between our data and the Uber model. So to summarize and to conclude, we have excluded a large portion of the array parameter space. In particular, the array-based fit point is excluded at more than 99.9 confidence level. We have a measurement of a almost pure uranium-5 reactor, which give a result consistent with the array deficit. And we have the unfolding of the spectral shape, which gives indication of a 10% spectral distortion at 5 MeV with respect to the Uber model. We plan to continue data acquisition until the end of this year, and we expect more than 300 days of reactor on, which is twice more statistics than presented today. You can see here is the expected sensitivity with the 300 days of reactor on. And as Chani mentioned yesterday, there is an ongoing joint spectrum analysis between Prospect and Stereo collaboration, so stay tuned for the results. And so you can find a lot more details on the result I presented you today on arXiv for the oscillation result and for the absolute rate measurement. And also, since the last ICHEP conference, we published a paper about the improvement of the gadolinium cascade simulation that you can find a reference here. I thank you for your attention, and I'm ready to hear your question if you have any.
Thank you very much. Thank you for the nice talk. And I think, so questions? So I do have one question. I think when we're waiting for others to raise their questions, my understanding is in the result you showed for the uranium-235, the deficit agree with what average, which is about 5%, right?
You mean for the absolute rate?
Uranium, right. So the rate. I remember from Anfeng Peng for the diabase spectral measurement, he mentioned that the uranium-235 compared with the theoretical prediction, it's about like 80% deficit. So how can I understand these two numbers? Can you comment on this?
I think this is related to the thing that
yeah, maybe I can comment, sorry. I mean, now in diabase, we see a deficit for the latest result, we see like 8% for the spectrum decomposition. We just see 8% deficit for uranium-235, not 80, just 8.
Yes, 8, sorry.
Yeah, so, and then I think here they mentioned the red point, sorry, the green point, they have, it's not the latest result, this is the latest published, and this is 92 point, yeah, so I mean, yeah, so we observed something about 7.8 to 8%. I think the latest result is 8%. Yeah, and the stereo just observed like 5.2, so.
So is there any tension between these two numbers?
I think, well, uncertainty-wise, it's not very far. I don't think there is really a tension here.
But these two numbers, these two different conclusions, right? If you say uranium-235 has, say, 8% deficit, that means that the major deficit comes from uranium-235, other than that, other isotopes. So, well, I guess, okay. Okay, I guess the error right now is a little bit high. Thank you. Other questions? I think I see. Okay. I don't see any other questions.
Yeah, so I just, sorry, I cannot again raise my hand. I just have a comment. I really think, I really like your results. I think, yeah, congratulations to this. And especially I really like the spectrum measurement and this 10% excess. I think it's very impressive. Yeah, so yeah, just congratulations. I don't have question. I just have a comment. So yeah.
Okay, thank you. I think the time is out. So thank you very much. And let's go to next talk from Yufeng Li, reactor neutrino anomalies and the possible solutions.
Yeah, can you hear me?
Yes, please.
Yeah. Okay, I will share my screen. Okay. So you see my screen? So hello, Jun, can you hear me?
Oh, yes, please go ahead.
Yeah, okay. Okay, thank you. So good morning, good afternoon, good evening, everybody. So we have heard several talks on reactor neutrinos, in particular for the reactor rate and the spectrum measurement. So here is my theoretical talk about the status of the anomalies and also the possible studies on towards the solutions. So next slide. Sorry. Okay, sorry. Okay, so
not moving. Your next slide is okay. Here comes.
It's okay. So the fundamentals of the reactor neutrinos have already been discussed by other talks. So I will skip this. So I will go directly to my main body for the rate and the spectrum measurements and what our study in these two aspects. And finally, it's my summary. So first, as we all know, for the reactor neutrino flux prediction, we have two different methods. The first one is the so-called summation method or ab initio method. So for this one, we need to rely on nuclear database and rely on the spectra for single beta decay. So you can see from the formalism, we first need the spectrum for one beta decay, and then the branch ratios, the fission yield, and all the other fission fractions. So finally, if we sum up all these contributions together, we will get the final spectrum. On the other hand, there is another semi-empirical method, the so-called convention method. So for this one, we use a beta spectrum measured in 1980s as a benchmark and to use around 30 virtual branches to convert this beta spectrum to the neutrino spectrum. So the so-called Huber plus Mueller model for the uranium-235, plutonium-239, and 241, all the three isotopes are used convention method, and the fourth one, the uranium-238, is using the summation methods developed by Mueller and his collaborators. And then this is one reminder for the measurements. We have first the consistently depth state for the reactor rates measurement from the inverse beta decay reaction, and the depth state is around 6%, as you already know from previous talks. On the other hand, for the spectral measurement, there is not a depth state, but the excess at around the 5 MeV range for both the current oscillation experiment and even more, for example, Prospect, Stera, and others. And first, we want to see the rate anomaly. And first, let's see the rate data. And for this slide, you don't need to read all the numbers, but I want to show you in the next slide, slide 6. For the left plot, you can see we grouped the reactor rate experiment in two different groups. For the first one, it's research reactors like Stera, as we just discussed. So it's mainly the uranium-235. For the other group, it's the commercial reactors. So it's have 4 different isotopes, and the contribution is their combination. So if we observe different depth state of the for different group of the reactors, so it means the contribution is from the miscalculation of the prediction. If we think it's all the different reactors have the same depth state, it may indicate it's a common reason, for example, the short Pelletan oscillation. Another factor is to classify the experiment is the baseline. As you know, if it's due to the neutrino oscillation, it will have the baseline dependence rate deficit. But now it seems there are also no this trend in the near range, for example, in the several tens of meters. So when we combine all the data together, we need to compare these two different hypotheses. For example, first is there is some problem in the 235, or there is the reason because of oscillation. Because this is a non-nested model, also we need to do the Monte Carlo simulation to do the statistical assessment. And as we show in the right plot, you can see it seems both hypotheses are consistent with the data. And if we do the assessment, we can see the oscillation is slightly favored at around 1.7 sigma. What's more, is the new data from Diaby and Reno is not only measure the total rate, but also measure the rate as a function of the fission fractions. You can see the comparison between these two experiments. Interestingly, for this measurement, there's one new measurement. The first one is the deficit compared to the prediction showing in the vertical shallow bands. So you can see the total rate is smaller than this, and also the slope of this curve is also not consistent with the model. So by combining these two experiments together, you can see both experiments show the deficit is because of the 235, not because of 239. So this measurement provides a new information for the reactor rates data, and it seems this is not consistent with model prediction. The confidence level is around 3 sigma. So by combining these two different group of data together, the rate and the evolution, field evolution data, actually we tested all the possible hypotheses with one deficit of one particular isotope, or with 2 or even 3, and also because of the oscillation, and even finally the hybrid hypothesis for combine these two together. After the analysis, we have the following three conclusions. First is a common increase of all the beta convention. That means the 235, 239, and 241 are equal. It means it seems it's not a problem of the convention itself. If the problem is because of these three isotopes, it's because of one single isotope, not all of them. Another is no matter what kind of hypothesis is, it seems a deficit of 235 is always favored. So this is also can be seen from single experiment, for example, Diaby and Stero. No matter what the size of the deficit, it seems this should have some problem. Another is if we want to see the oscillation, it seems there's no conclusion on this. It can, including this and excluding this, they are all agree within 1 or 2 sigma. To test the oscillation, actually, one need more different data. Here, I want to show the beta decay data. For example, the Catherine data last year, one can see it can, because we know if there is one stellar neutrino, there will be a kink in the spectrum, and if with the data, we can constrain the high mass square difference range, because for the high mass range, it will have more rate, so the uncertainty is smaller. So it will have even better constraint on this range. So for the beta decay data can rule out a large part of the high mass square range, and the low mass square range is tested using the so-called reactor spectral ratio data. It's ruled out the low mass range. So finally, actually, if the reactor anomaly is because of oscillation, actually we already rule out a large part of most of the parameter space, leaving only a small range. And in the future, for 3 years culture, it will even better. The second topic for me is about the spectral anomaly. So first, I want to show the study on the summation method. So in the summation method, many different groups already studied this and identified different problems. For example, there are some incomplement and also the bias in the database. For example, in these two different databases have different results. And also for the some nuclear data measurement problem, the pandemonium effect shown here. And for single beta decay, there are also some problem. For example, the contribution of forbidden decay is still unknown or have large uncertainty. Also, we need to know the accuracy of the different approximations, which I will show in the next slides. So here we want to test the usual approximation in the beta decay spectrum formalism is valid or not. So in the usual case, it can, for this analytical calculation, can reproduce the lifetime very well, but actually there's no test for the spectrum. So in this calculation, in this paper, we use exact lifetime wave function calculation. It's a fully numerical calculation, and we do the calculate the final beta spectrum and the neutrino spectrum and test it with the analytical one. So here we consider three different effects. The first is what's the famous Fermi function, and the approximation is how accurate for this. Another is a finite size correction. Finally, the neutrino wave function approximation. So here is our result. Here I listed our assumption. We used the ENDF B8 and also the struct data in SDF for the decay data, and also for the single beta decay, we use the full numerical calculations. From this plot, you can see, compared to the analytical one, it seems there is access for the neutrino spectrum for all the four isotopes at a similar size, and it's increased as the neutrino energy increases. So the size of this is at around 6 MeV, it's around 2%. And also for the electron spectrum, it have a deficit, and the size is around 4%. So here I want to remind the spectral anomaly is compared to the convention method. So if we use the convention method for the same effect, because we are tuning the beta spectrum, so all the deficit and the excess will contribute to the bump. Finally, the third study is study the convention method, but we include the forbidden decay contribution using the shape factor. Here we use the full relativity calculation for the shape factor, shown here in the dashed line. So to first study, we need some statistical information about the nuclear database. For the left plot, you can see for different energy endpoint, the contribution for the allowed and the forbidden decay are different. Interestingly, you can see at around 5 MeV, actually, the allowed decay and the forbidden decay are comparable. So another thing is the effective charge from the database. You can see for the forbidden decay tends to have a larger effective charge compared to the allowed one, shown in the red line and compared to the blue line. So based on these two different statistical information, we can do our convention method, because we first pick from the high energy range, we pick an endpoint and do the statistical sampling based on our previous histogram. So we determine is allowed to decay or forbidden decay. Then if it's forbidden decay, we will use the shape factor for different transition type, for example, GT0- or 2-. So based on this calculation, we get the neutrino spectrum and the beta spectrum. This is the comparison with using for the EU235 beta spectrum. You can see if it is 0-, it seems it's consistent with the allowed one within 1%. But if it is a 2- type, actually for the neutrino spectrum, it's showing a very wide axis in the high energy range from 4 MeV to 6 MeV, and the size is around 4 or 5%. So it means it cannot reproduce the bump itself, but it seems it can compute somehow some of the excess in this range. So there are also other studies for forbidden decays in these two papers you can see in my backup slides. So finally, it's my summary. The reactor rate and spectral anomaly are based on the reactor models developed in 2011. So somebody concerned about this problem because there might be some new physics in this study, for example, the stellar neutrino. But before this, I need to know the standard physics interpretation. For the reactor rate anomaly, we use the global analysis of the order flux or the rate data. It seems no matter what kind of assumption we use, there is a deficit in the 235 flux. And also, but we don't know other contributions, the size of other contributions, is from other isotopes or from the oscillations. So for the oscillation, we need the model independent method, for example, using the beta decay data or using the reactor spectrum ratio data. I think also studied in the previous talks. For the spectral anomaly, actually, there are many nuclear physics issues are examined. So as I was showing in my previous slides, there are some trends showing there are some excess, but it cannot fully accommodate this bump size. So it's still an open question. Thank you very much for your attention.
Thank you, Yifeng. Unfortunately, I don't think there's any time left for questions. So we encourage everyone to, anyone who have questions to go to the Mattermost channel. So we will have to go to the next talk, which is first the result from the solid reactor neutrino experiment from David Hanaf. David, would you please share your screen? Yes.
Yes, I'm sharing the screen.
Okay, thank you. Please. Yes, we can see it. Can you just go ahead, please? Thank you.
Okay, hello everyone. So I will give today a status of the solid experiments. Measurement of antineutrino coming from nuclear reactor have shown one anomaly on the flux and a distortion in energy. A global deficit of the measured flux compared to the prediction have been seen, as you can see on this figure. It could be explained by a new oscillation into stellar neutrino. This is called the reactor antineutrino anomaly. Also, the GALEX and the SAGE solar neutrino experiments have shown in their calibration data the same discrepancy. The distortion on the energy antineutrino spectrum have been seen by the θ13 experiments. This is the so-called 5 MeV bump. And the Diabe collaboration pointed out that one candidate could be the uranium-235. The solid detector is based near the reactor, the BR2 reactor at SICA-Sen in Belgium. This is a research reactor with a highly enriched fuel in uranium-235. We have a compact core, and the detector is placed at 6 meters of the core. We have also a low gamma and neutron background from this reactor, and we have low overburden. It implies an important cosmic induced background, and this was a key challenge that gathered solid design. The detector main feature is to combine the two kinds of scintillator, the PVT and the ZNS mineral scintillators. It allows us to have linear energy response and highly segmented targets, but the price to pay is to understand a complex detector and a new technology. The target is made of more than 12,000 cubes arranged in 50 frames. The solid cube is a combination of two scintillators, the PVT cubes for electromagnetic signal and two lithium-6 ZNS screens for neutron capture. The scintillation photons are captured by more than 3,000 wavelet-shifted fibers and read out by MPPCs. We also have passive shielding made of water bricks and polyethylene to mitigate the fast neutron background. The signal that we are looking for is the inverse beta decay, which is the interaction of an antineutrino with a proton giving a positron plus a neutron. We first start by exploiting spatial and temporal coincidence between the prompt signal, which is the interaction of positron plus the two annihilation gammas in the PVT, and a delayed signal, which the capture of the neutron on lithium inside the ZNS. But beyond the spatial and temporal criteria, and thanks to the high segmentation of our target, we can exploit the detailed topology of the prompt signal, which is given by annihilation gammas. But the capital issue of solid detector is to control two backgrounds. First, we have the cosmic induced background, which is proton recall that mimic the prompt and delays that have the same features as IBD. It impacts all the IBD energy spectrum. The second background is the BPO background. It is an unexpected and critical internal contamination of the ZNS layer. It's nearly 2 orders of magnitude above IBD before selections. The beta decay of BPO is mimicking the prompt, and the alpha decay of BPO is mimicking the delayed signal. It's impacted the IBD spectrum up to 3 MeV. We have designed a specific variable called the B-punisher using a pulse shape discrimination techniques in ZNS centimeter by comparing waveform of alpha and neutron interaction, as you can see on this plot. In both cases, the space and time prompt delay distribution are close to IBDs. This makes the control of them even harder. We firstly, at the first attempt, design a basic selection using only prompt and delay space and time coincidence. The reconstruction of prompt topology is done by, is given to find a list of cube positions and energies that minimize the likelihood to measure the given set of fiber signal above 200 keV. We use sequential CRET, and we only use those variable and looking at prompt energy between 2 and 7 MeV. We have this kind of discrimination for those variables. We reach this level of performance. We need something else. For that purpose, we will use the topology of prompt to be competitive, and this is given by adding information coming from annihilation gammas. Those information are low energy deposits and back-to-back behavior. But there are challenges. We have to lower the fiber analysis threshold from 200 TeV to 100 TeV. It implies also to understand the detector response in deep details. We have two approaches to reconstruct annihilation gamma. Firstly, we split the detector in 2 hemispheres, as you can see on this scheme. And secondly, we do a tracking by minimizing the likelihood of cube positions according to the cross-section. Then we have access to new variables, the energy of gammas, the angle between those gammas, and so on. You have the new discrimination power of those variables, for example, the energy and the dot product here with the back-to-back annihilation gammas. We have improved the previous selection by selecting those annihilation gamma, and thus we improved the background rejection by roughly a factor 2. But this is again not enough. To do better, we have to use MVA to better exploit topology. For that purpose, we needed to bring our understanding of the detector to the necessary level, and this is given by calibration data. We use 4 gamma sources for calibration: the cesium, the bismuth, the sodium, and the americium beryllium. We firstly have a look at the cube light yield homogeneity, and we found 3%, as you can see on the top. We also have probed the linearity response of the PVT centimeter, and we have measured the neutron detection efficiency found at 52% using 2 sources, americium beryllium and californium. We have done a precise Monte Carlo tuning. We have taken advantage of the BPO background to control first the reconstructed energy, especially for tuning the light leakage between cube to cube, and the topology, because the BPO could be followed by radiative decay. The sodium-22 source is used to tune the PVT energy in the simulation and control the energy below 1 MeV. You have example of the data MC agreement that we reach on the BPO and in the sodium-22 in calibration runs at different reconstruction level. We also have cross-checked that the new introduced topological variables have a good data MC agreement using the BPO background. And you have here the number of cube and the energy of the for the 2 gammas, and also the dot product of between the 2 gamma. Then that we have reached a sufficient confidence in our simulation, we can use a multivariate analysis. We have developed two independent approaches based on commonly used MVA tools. Firstly, a uniform boosted decision tree. This is a tool designed to optimize the discrimination while keeping uniform efficiencies. In our case, is as function of the prompt energy and the baseline. As you can see on those plots, we reach a flat, we have a flat response of our selection within 20%. We also have designed a TMVL neural network to cross-check the uniform decision, boosted decision tree. You have example on the top of the discrimination power to go from the 0 gamma category to the 2 gamma category. The both approaches are trained in category and the same variables as previous, and we use the same variables as previous analysis. The gain of such approach is to have reduced the background again by a factor 2. And you have a summary plot here, which is the background over signal as function of the excess and the improvement by using topology and multivariate analysis in simulation. Now that we have optimized our selection, we can look at real data. We have two backgrounds with a different day-to-day evolution. The BPO may change because of radon release, and the fast neutrons are correlated with pressure variation. The first thing that we have done is to have a highly enriched BPO selection. We do that by flip the BPO initial cuts. Then we select, we remove accidental, from the two selection, IBD and BPO, and then we can subtract the BPO contamination in the IBD selection. It remains only fast neutrons. Then the fast neutron rates could be modeled. We can model the fast neutron rate dependence as function of the pressure. This is done on this figure with a linear fit. We can thus subtract the fast neutron background in the signal region, and we can see the excess, which are the neutrinos. We also have cross-checked that the excess extracted as function of the neural network cut is in agreement with our prediction, as you can see on the bottom left figure. We also have evaluated the neutrino excess and the S over B in real data and cross-checked that this is consistent for all the selection that I have previously presented. You have the summary plot on this on the top, which is again the background over signal as function of the excess. You can see that in blue the prediction and in red the extracted numbers from data. And you can see that they are in well agreement for when we are not using topology, when we are using topology, and when we have topology plus MVA tools. We also have cross-checked that the neutrino excess is in agreement with our prediction in energy and baseline. So after subtraction, we compare the excess with the simulation, and as you can see in energy and in position, we have a good agreement. And to go further, we need to improve the efficiency to see annihilation gamma because our selection is based on that. For that, we have upgraded the detector with a higher light yield. Taking advantage of the new generation of MPPCs, which have a better probability detection efficiency and lower crosstalk, we have demonstrated that we will have a gain of 40% in light yield. We already have dismantled the detector at the beginning of July, and we are currently replacing all the MPPCs of the detector. We also have improved the B-punisher, which was a simple ratio by developing a one-dimensional conventional network, and we expect to reduce a BPO background by a factor 2 or 3. So to conclude, SOLID has to face a very challenging background condition. We have cosmic-induced background and an expected rate of internal BPO background. We have focused on exploiting the annihilation gamma topology thanks to our high segmentation. We are also working hardly on systematic studies, and the upgrade is coming soon. So stay tuned, and thanks for your attention.
Thank you for the nice talk and the questions. Would you please raise your hand? Okay, I have one. Let me see. This time I should be able to find it. Oh, Sunny, right?
Yes. Hi.
Yes, please.
So you listed the your backgrounds here in the conclusion. So what is the main background among those? Which is dominant?
So after selection with MVA tools and the topology, it's a 50-50 background. So we have 50% of BPO and 50% of fast neutron.
Fast neutron, I see. Okay, so thank you.
Thanks.
Thank you. So the fast neutron, because your overburden is so low, right?
Yes, it's between 6 and 8 meters.
Okay. Okay. Thank you.
Water equivalence.
Okay. Thank you very much. Let's go to next talk because we are a little bit late. So let's go to the next. Thank you very much, and let's go to the next talk, which is atmospherical neutrino oscillation with superchemiocondy. From Volodymyr Takhistov.
Hello.
Hello. Yes. Can you share your slides? Thank you.
Let me try. Can you see?
Yes, I can see it.
Okay.
Please
great.
go ahead.
So thank you very much for the opportunity to give this talk. I'm Volodymyr Takhistov from UCLA, and this will be on atmospheric neutrino oscillations with Super K. And by the way, this is a picture I took inside the Super K during the upgrade, and you see Super K looks great. So let me start by briefly describing the state-of-the-art neutrino observatory, Superchemiocondy. Now, the experiment is 22.5 kiloton fiducial volume, 1 kilometer rock overburden, inner and outer detector, and 5 run periods, totaling about 20 years of data. And right now, something very exciting is happening, is that we have gadolinium loading, and we'll hear more about this later. But it cannot be overstressed how amazing experiment it is. It is a very great multi-purpose physics laboratory. First, you have a very big energy range that you cover, and second, you cover a very large amount of topics. Solar neutrinos, atmospheric neutrinos, supernova, diffuse supernova, dark matter, and there's also various dark matter and direct detection things that you can do here. Proton decay, baryon number violation, and other neutrino astrophysics. And also you can do various exotic things such as look for cuboles, monopoles, and so on. So this is really great. And of course, the discovery of neutrino oscillations. Okay. Now, the detection technique is Cherenkov ring imaging, and on the left side right here, you can see a schematic from Ed Kearns that the neutrino comes in and interacts, and you get a Cherenkov ring that you can then detect with PMTs. On the right-hand side, you see basically what the events that Super K detects. You have the showering events right here that are E-like, and they come from the E plus minus and the gammas, and the non-showering like, without an E and M shower, from the muons and pions. And what is very nice is that these are actually real data events from 1998. So this is very exciting. Okay. Now, let me jump into atmospheric neutrinos. So cosmic rays interacting with the atmosphere result in very many neutrinos. And here on the right, you can see a schematic. You have isotropic flux of cosmic rays coming in, hitting the atmosphere, producing mesons, and then you will have a bunch of neutrinos. And what is great about this is that this is basically an atmospheric collider, or more precisely, atmospheric fixed target experiment that is always on. So you do not have to worry about the beam being on and off. And the propagation baseline ranges from 10 to 10 to the 4 kilometers, depending on where the neutrino is coming from, so you can take advantage of that. And here on the bottom, you can see various calculations of the flux, the three leading ones, Honda, Fluke, and Bartol, of what do you expect. And so you see that the energy, typical energies, energy ranges that you expect for atmospheric neutrinos of order from basically from MeV to TeV. Yeah. So the atmospheric neutrinos experience Earth matter effects. And as you can see right here on the previous page, I didn't mention this in detail, but as neutrinos propagate through Earth, as you can see, they will encounter different layers within the Earth. And different layers can be characterized very simply by just different densities. And so this will affect the neutrino propagation. In particular, as you go as you pass the mantle, the core, and so on. And so you will experience Earth's matter effects, the Earth's MSW effects, which modify the effective Hamiltonian for neutrino propagation by the basically this term, which depends on the density. So as you go through different layers, you affect the propagation. And for antineutrinos, you change the sign. Now, just looking, as you go through the equations, you will see that as you change the normal inverted hierarchy, this will reverse the effect of neutrinos versus antineutrinos. And here is this effect, how it actually is visible from the 2018 Super K publication. And the atmospheric neutrino oscillations are sensitive to hierarchy, theta 2-3, and delta CP. And so then you can do a fit and look what you get for these parameters. Okay, I would like to note, I would like to also note that Super K has detected new tau neutrinos from mu oscillations, as pointed out in the 2012 PRL, and more recently actually measured the cross-section from the updated 2018 analysis. So this is also very nice. And actually, the atmospheric neutrino analysis is quite a in-depth fit. You have more than 15 data samples for the full 3-flavor combined fit and more than 150 systematics. So this is a very in-depth analysis. And here are the just a preliminary view of the very recent fit. And here is the what exactly is the update compared to the previous Super K results of the full fit. So the current results that will be shown, they correspond to full SK1 to 4 lifetime, corresponding to exposure of 365 basically kiloton years. And this is compared to 328 for 2018 SK published result. And this is this paper right here. Now, the main improvements in the analysis itself come from neutron tagging efficiency, of efficiency of about 25%. And this helps for new bar separation. Right. And also, there's a new boosted decision tree-based selection for motoring events, which increases signal efficiency and sample purity. Now, here is a particular illustration of how the hierarchy would be affected. It's not very obvious, but this is how the various data bins would affect it. This is basically up and down asymmetry. This corresponds to different cosine and zenith angle. And so as the data moves around, you can see that the different bins will be affected for the normal inverted hierarchy and how it will look. Here are the preliminary results of the combined fit. So you can see that SK data disfavors inverted hierarchy at basically 70 to 90% confidence level. And this is to be compared to the SK 2018 published results, which disfavor at a somewhat stronger level. Okay, so the preference for normal hierarchy slightly decreased. But again, if you look specific at a specific data samples, it's there's many bins that can affect these results. Additionally, SK data prefers first octant of theta 2-3 and the delta Cp of 3 pi over 2. Okay. And these three quantities are the three pillars of what we want to determine from the atmospheric fit. Okay. Here are the combined results projected on a 2D plane. So here is the SK 2020 updated analysis, which I'm describing. And here on the dashed, you can see the SK 2018 analysis. So the counters have slightly moved around, but the overall region preference is stays similar, right? Now, I would like to point out that atmospheric neutrinos don't just do these three parameter fits, which I just described, to do the hierarchy, the octant of theta to 3 and the delta Cp, but you can also do other exciting things with them. And actually, they provide great opportunities for BSM studies. In particular, I would like to mention non-standard neutrino interactions. So there are many experts in the audience, but just briefly, various BSM theories can have extended gauge symmetries beyond the standard model, SU3, SU2, and U1. And you can also have an extended particle content. And quite often, depending on the model, you will have non-standard neutrino interactions because of this. And so this will affect the propagation in matter by these additional interactions. Forgetting about the model specifics, you can take a phenomenological approach and parameterize all the possible additional interactions as basically 4 fermion operators with 2 neutrinos and 2 other fermions. And this will basically add a 3x3 non-standard interaction matrix to your Hamiltonian, which I was showing before. And these are these NSI entries. Now, SuperK has different sensitivities to different entries, but you can fix the oscillation parameters to the SuperK best fit, which I just described previously without the NSI, and then see what comes out for the new parameters. And this is basically how the analysis is done. Here on top, on the right up, you will see preliminary results. And this is how this compares to the old results as shown on the right on the bottom. So the new results are for SK1 to 4. And again, these are preliminary results. And the older results are only for SK1 and 2 from the 2011 publication. So there's a very slight preference, but there's no significant evidence for any such effect. Now, and of course, you can try to do other modifications of the interactions beyond the NSI, but you can do a lot of things, a lot of great things with atmospheric neutrinos. And I would like to briefly mention, before I conclude, that the future is very bright for SuperK with SKGD, and we'll hear more about this in the upcoming talks. So I will just very briefly touch up on this, that right now, I'm sure you have heard, SuperK is being loaded with gadolinium, and the purpose is to transform already great experiment into a very powerful astroparticle detector. And the main benefit is you will improve neutron tagging efficiency from 20%, roughly 20% on hydrogen to 90% on gadolinium. And please see the talk by US on all of this in more detail. And once you improved this tagging efficiency, that means that the neutrino interaction, like shown right here, you will be able to look for the coincident signals and clearly see. Now, the main purpose of this is, as we'll hear in the next talk, is a first detection of diffuse supernova neutrino background. But I would like to point out that even if this is not seen, this will still provide amazing information about astrophysics. So this is great either way. And additionally, you will also suppress atmospheric neutrino background for proton decay, because for usual proton decay signals, you usually do not expect many neutrons. And SuperK already being the best proton decay experiment, this will push this even farther. And of course, there is a lot of benefits just for the standard atmospheric analysis, such as neutrino to neutrino separation, which right now is done with basically 25% efficiency tagging, but this will be improved, and additional other benefits. So there's a lot of exciting things coming. So let me conclude that after neutrino oscillation discovery, it is important to pin down fundamental oscillation parameters. Super-K is the leading neutrino observatory, and atmospheric neutrinos provide a fruitful arena for exploring these further. Now, the new Super-K results, and again, this is preliminary, are that the data disfavors inverted hierarchy at 70 to 90% confidence level and prefers theta to 3 first octant and delta CP 3 pi over 2. Additionally, using atmospheric neutrinos, Super-K can broadly search for any kind of modifications of the oscillations interactions beyond the standard ones, such as NSI, which I mentioned, and we see no significant evidence. And we expect improved results with very new and exciting SKGD experiment, which we'll hear more about later. Thank you very much.
Thank you very much. Thank you for this nice talk, and congratulations on the new result. And we have time for question. So if you have question, please raise your hand. And I see, okay, so there's one question on slide 13. Fix oscillation parameters to SK best fit with no non-standard interaction. Would you please explain this with Super-K best fit you use?
Yeah, so previously I mentioned that because of the matter effects and things like this, the atmospheric Super-K fit is basically sensitive to hierarchy, theta to 3, and also the delta CP. So you fit together these quantities and you get some numbers, and this is what is the official Super-K result. Now, then you can add additional quantities like this, like the NSI, or you can add Lorentz relation, or whatever you want. And then you can ask, given the best fit parameters without these additional quantities, what can I say about them? So, and then you can perform the fit and ask for that.
Okay, thank you. Just this question is from Emia. Sorry, I forgot to mention the name. Okay, so I think we are running out of time for this talk. So thank you very much.
Thank you.
And let's go to next slide, the next presentation for the diffuse. So the diffuse supernova neutrino background in superchemical from Sonia L. Hendry.
Hello. Okay, let me start the video and the screen.
Great, we can see your slides, but it's not full screen yet.
Oh, I just put it full screen. Do you see it now?
Not yet. Maybe there's a delay, but.
Okay, that's strange. I'm definitely in full screen.
Maybe because of the network, somehow I cannot.
No, I cannot see it either, and I propose you do now. Full screen, do full screen and then share. If you can unshare, do the full screen and share, I think we would see the full screen then.
Yes, but I'm not sure that I will be able to see the Zoom window once I have the full screen. Yeah, now I cannot share anymore. I have the full screen.
Well, do you mind turn off the video first to see?
Yes.
It might be the network.
Yeah, let's see. So I share without the full screen. Now I go to full screen. Does it work?
No.
Okay. So
oh, yes. Okay, hold on. Yes.
Okay.
Somehow, hold on 1 second. It was, but then it come back to the non-full screen again.
Yeah, it's because I removed it, but then I put it back. So maybe in a few seconds.
No, it doesn't come back.
Okay, so let me.
Oh, hold on. Yes, it's come back.
Oh,
well, somehow when you turned off it.
Each time I turn it off, then it goes back. So okay, here it's
right.
back.
It's Oh, there are two options. Whether either you do it this way or you let me to show the full screen for the audience. I think this way it's okay, good too. It's just big enough.
Okay, let's do it this way. Sorry for the delay. Okay, so hi everyone. I'm going to present the latest Super Kamiokande preliminary results for the diffuse supernova neutrino background. Okay, so what is first this mysterious DSNB? Core collapse supernova bursts emit a gigantic amount of neutrinos, about 10 to the 58 of them. However, experiments on Earth are only sensitive to galactic supernova, which are very rare. So if we want to learn as much as possible about supernova mechanisms, we have to consider the accumulation of neutrinos from distant supernova, which we call the diffuse supernova neutrino background. And this DSNB contains unique information about neutrino emission spectra. So you can see, for example, that it allows to infer the fraction of supernovas that end up forming black holes, like the purple arrow on the plot on the right. The DSNB also allows to understand the history of star formation, which is the overall normalization of the different spectra you can see here. And it contains information about the universe expansion. However, this signal is quite elusive and it is relatively low energy. So now we're going to need an experiment that has a low energy threshold, decent resolution, and is large scale. And so we can use, for example, Super Kamiokande. Super Kamiokande is a 50 kiloton water Cherenkov detector, 22.5 kiloton fiducial volume located in the Kamioka mine in Japan. The water is constantly purified and we have more than 10,000 photomultipliers on the inner detector. This allows for an energy coverage that ranges from 4 MeV to TeV scale. And currently, as was mentioned, SK is being doped with gadolinium. So this is a very exciting phase, but data is a bit fresh. So here what I'm going to present is data from phase 4, which is the longest data taking period of Super Kamiokande. So what can phase 4 do for us, for the DSNB? Well, the most obvious way to see the DSNB Super Kamiokande is to consider inverse beta decay, IBD, which is the interaction of an antineutrino with a proton, giving one positron and a neutron. In principle, this IBD is very characteristic, and if you were able to characterize it fully, like in the plot on the right, you would see a very nice sweet spot for the DSNB between 10 and 20 MeV in Super Kamiokande. However, life is not that simple, and what you are going to see is a prompt signal from the positrons that we typically investigate between 12 and 80 MeV, and that is easy to find, and a very weak delayed signal for the neutrons that before Super Kamiokande 4 was not even picked up at all. So in practice, the backgrounds you have to deal with are overwhelming and come mainly from cosmic muon spallation, here at low energy, and from atmospheric neutrinos at high energy. So for an efficient search, we need to characterize spallation and atmospheric backgrounds and absolutely identify the neutrons. For this reason, the DSNB analysis will rest on 3 main pillars. First, dedicated analysis for spallation cuts. Second, dedicated analysis to characterize and reduce atmospheric backgrounds. And third, neutron tagging that has been possible only since SK4, so it's quite new. Let's start with spallation. Spallation backgrounds come from radioactivity induced by cosmic muons passing through the detector. They take place pretty much every 2 minutes, which means that they have to be considerably reduced if we want to see the 5 to 20 events per year of the DSNB. Fortunately, for later, most of the signatures do not involve neutrons. In less than 1% of the cases, we also have a more problematic signature that has a neutron, mainly coming from lithium-9. So why we get rid of spallation is by considering correlations between potential DSNB candidates, low energy events, and preceding muons. However, these correlations occur over very large timescales, and we cannot model them using simulations right now. So spallation reduction strategy will operate with 2 steps. First, preselection steps where we identified clustered candidate DSNB events and neutrons from muon showers. And second step, where we investigate correlations between muon and DSNB candidate events. The way we investigate correlation is that we pair each DSNB candidate event with muons up to 30 seconds before. So for one event, we have 50 pairs to consider, about 50 pairs. And for each of these pairs, we investigate correlations using a likelihood analysis based on the following 4 variables. So we consider time difference between the two events, distance to muon track, and also the muon shower, the profile of the shower induced by the muons. Who says likelihood analysis also says distributions. So we extract spallation distributions directly from data by comparing our data pairs to random pairs where the muon and the DSNB candidate are definitely uncorrelated. You can see the extraction process here for the distribution of the transverse distance to the muon track on the right of my slide. This procedure allows to remove a bit more than 90% of the background, which is not enough. The good news is that it's much more efficient for the problematic lithium-9 signature. And then we're having about 40 to 90% signal efficiency, depending on the reconstructed energy. So we'll go back to how to improve spallation further, but first, let's consider atmospheric neutrino backgrounds. Atmospheric neutrino backgrounds can come from either neutral current interactions that produce one or more gammas, and charged current interactions producing a bunch of charged particles. These gammas and charged particles give rise to specific light patterns in SK that allow us to categorize backgrounds. And since life is difficult, sometimes, more rarely, we're having neutron emission too. So we are now having 4 categories of atmospheric backgrounds, 2 reducible and 2 irreducible. And for the reducible backgrounds, we have a series of high signal efficiency cuts based on the Cherenkov light pattern. And these cuts allow us to get the spectrum, atmospheric spectrum on the right, which brings us to another problem, which is that atmospheric neutrino simulations are associated with large systematics at low energy. So here we can mitigate the systematics somewhat using sidebounds, for example, but what is going to really save the day for the DSNB analysis is that the decay electron spectrum, the Michel spectrum, can be measured directly from data, so very well characterized. So now I have presented dedicated spallation cuts, dedicated atmospheric analysis, and if I stopped there, this would not be very qualitatively different from analysis in SK123. However, SK4 allows for something new, which is neutron identification. So neutrons are being seen because they are captured on water after some time, some long time. And in SK4, you can see it because we have added to this SHE trigger for the positron and a large AFT trigger window where we can look for neutron capture signals. However, these signals are tiny, so looking for them amounts to looking for a needle in a haystack. But looking for a needle in a haystack is possible if you have a good enough magnet. And here our metaphorical magnet is that neutron capture occurs near the positron vertex. This fact allows us to do a time of flight subtraction, which will concentrate all the photomultiplier hits associated with neutron capture in a 10 nanosecond window. So after a basic preselection cut for this 10 nanosecond window, we can identify neutron candidates. And these neutron candidates can then be individually analyzed using a boosted decision tree. And here you can see the performance of this boosted decision tree. This allows for excellent background projection power, but you pay some price in signal efficiency, I was mentioned in the previous talk. And what you are going to see in the next talk by Luis is that you are going to have considerable performance enhancement for this neutron identification after gadolinium doping. So now we're having neutron tagging, dedicated spallation cuts, atmospheric cuts. So we can perform 2 types of analysis. The first one is a supernova model independent analysis, that is an exclusion bound optimized for different energy bits. Here we perform at low energy and we try to reduce systematics and atmospherics, which in practice will mean that we'll have larger energy bits. The second type of analysis is a spectral shape analysis, so completely model dependent, that takes place at higher energy because we need to get rid of spallation backgrounds entirely. And here we rely heavily on the fact that the dominant background will come from decay electrons that are well characterized. So let's consider the supernova model independent analysis. And on the left, you can see exclusion bounds for 3 large energy bits. You can see, sorry, the backgrounds and the data for 3 large energy bits. On the right, you can see the associated limits on the DSNB flux and examples of predictions from a few models. So here, neutron tagging allows us to go to lower energies than before, 12 MeV now, instead of 16. And if you look at the last column of the table, high energy limits, and compare the observation to the Ando model, which is an optimistic VSNP model, you can see that we're getting quite close. So this is very encouraging for super-K gadolinium. However, one thing that we have to keep in mind is that if we want to go to low energy and make the most of SKGD, we need to understand the neutral current atmospheric backgrounds that are associated with large systematic uncertainties. So now let's move on to the spectral analysis. So here I'm going to present it for one model, which is this Ando very optimistic model. We perform spectral fits over different Cherenkov angle regions and with neutron tagging and without neutron tagging. So here are very preliminary results. On the right, you can see corresponding likelihoods for the analysis without neutron tagging, which is the dashed line, with neutron tagging, that is the dashed dot, and grayed out in the background, I have added the results from the previous phases of SK. And now the solid black curve corresponds to the combination of all of this. And if you look at the combined result, which is the last line here, we see that the limit on this Ando flux, 2.7 centimeter, 7 per second, 2.7 per second per centimeter squared, is close to the prediction, which is 1.7 per second per centimeter squared. So we are getting close here too. So let me conclude now. This was the first analysis of the diffuse supernova neutrino background with a full SK4 data set and with neutron tagging capabilities. You can see that the most optimistic models are getting very close. So there are very encouraging prospects for SKGD. However, one lesson to remember is that we will really have to deal with atmospheric backgrounds and in particular with neutral current backgrounds at low energy. And this could be done, for example, by separate intermediate detectors in Hyperkamiokande. So stay tuned for the near future, but also for the far future. Thank you very much.
Thank you very much. A time for quick question. If not, I think I will urge you to go to the Mattermost for your questions, and then we are going to the next talk. Thank you. Thank you for your presentation. It's a very nice talk. So next talk is status of the SKGD project. Louis Margot. Can you, sorry, from Louis Martin Margot. Can you please?
Can you hear me?
Yes, I can hear you.
Okay, can you see also my screen?
Not yet.
Not yet. Maybe it's coming because I am in principle projecting this.
Yes, I can see it. I think you can start. If you want to share your video, that would be great too. Thank you.
Okay, I don't know how to do that right now.
Okay, in that case, then we can start.
Okay, so thank you. So yeah, I will present the status of the Super-Kamiokande gadolinium project. And I was kind of scooped because you already know that we are already loading. That's a very good news, I think, because that's something we expected quite some time ago, the people that have been working in this project. I think I had the best introduction and motivation from Sonia. Also, Volodymyr introduced the Super-Kamiokande detector, so I will just briefly go on this. You have seen how tough it is to look for supernova relic neutrinos, and what can be good if we have an efficient neutron tagging. So once again, with gadolinium, what we expect is that the neutron capture will happen much faster than in just pure water, plus that the gadolinium produces a gamma cascade of 8 MeV to compare to the low energy of the single 2.2 MeV gamma produced on the neutron capture. So how much gadolinium we want to have in Super-K? Well, in the first loading, we plan to just load 0.02% of gadolinium sulfate. This will give us about 50% of all the neutron captures on gadolinium, being the other 50% is still in water, which we can still try to find, as Sonia has shown. Our final target is 0.2%, but that will have to wait for now. How does gadolinium sulfate look like? Is this white powder here that, in fact, once it's diluted in water, is basically transparent to Cherenkov light. So before injecting this stuff into SK, we wanted to make sure that it's safe to do so. So we started a R&D project called IGATS, evaluating gadolinium's action on detector systems already long ago in 2009. We checked actually many things to make sure that this would be safe. So IGATS was built using the same materials as in Super K. This is a picture of that hole. It's a 200-ton tank, which actually now is running as a standalone galactic supernova detector. This plot here is very busy, but basically summarizes a good deal from what we have seen in IGATS. So you have here the concentration in the IGATS tank here on the right-hand side of the scale. So you see here how we start loading it, and then we reach the final goal of 0.2%, and it stays constant. So the water system is not eating up the gadolinium, it's not disappearing. And on the upper side, we have the water transparency. In the blue band is the typical SK value. So you see that if we run on stable conditions, we reach SK values while we do not lose any gadolinium. Also very important, we checked even by eye whether we had any harmful effect on the detector, and we find none. These results and many more are actually published this year in 2020, so you can have a look if you want later. It's very interesting. There are many interesting things there. So anyway, before injecting this gadolinium sulfate into SK, we had to refurbish the SK tank. So we emptied and refurbished it. We cleaned the walls. We cleaned also the detector structures. Since it was already open, we replaced it inner detector and outer detector, PMTs, many other things were also upgraded or changed. We also had excavated a new hole to install the new water systems and water purification systems. We also modified the in-tank piping to have an increased flow of water inside the tank and increase the cleaning power of our water system. We also fixed the leak we had in the SK tank, so we do not leak any gadolinium into the environment. We observe no leak, has to be less than 20 liters per day. So here in this picture, you can see the very radio pure gadolinium sulfate that we are already injecting. This picture is showing the new cavern I mentioned before and the new equipment to dilute and inject clean also this gadolinium sulfate. So finally, we were ready to start loading and injecting. That happened on July 14th, 10:29. This is the moment when we change the run from SK phase 5 to phase 6. Happy people behind the masks. We here another picture when we started diluting and injecting gadolinium. Here people introducing the gadolinium into the water system for the first time. So how do we do this? So we take water from the top, we dilute it, dilute the gadolinium sulfate, to 0.02% in mass, and then we supply it from the bottom. The supply flow is about 60 tons per hour. It means that in roughly 35 days, we complete this task. So where are we now? We are around here, 30th of July. Here's the amount of injected gadolinium already. We are almost halfway towards our first goal of 0.02%. So the question is whether we can already see this gadolinium in the SK tank. The answer is yes. We have been sampling directly from the SK detector. In this case, I show you the inner detector. Here I show you the Z variable, which is Z equals 0 is the center of the tank. Negative values is the lower half of the detector. Positive values is the upper half. So you can see that the concentration quickly goes up and going from basically pure water where the concentration is 0 to a high concentration happens in say 2 meters. And also you can see the front how is going upwards in the detector too, in roughly 1.5 meters a day. You can also see that even in the loaded region, the concentration is not yet homogeneous, so we will not be able to compare later on with Monte Carlo. Nevertheless, in this lower half of the detector, we have already gadolinium, and we will look for neutrons, and that's what we did. We introduced an americium beryllium source surrounded by a BGO crystal, so that the 4.4 MeV gamma would make the BGO crystal to scintillate. That is our prompt event. And then we look for the delayed event, the neutron, being captured on gadolinium and producing this 8 MeV gamma cascade. So can we see this? We deployed this source in 3 different positions. Z minus 12 meters, that's in the lower part of the detector. Z equals 0 at the very center, and then plus 12 meters. By the way, this was done when the front was far away from the center still. So here you see the spectrum of these neutron capture candidates, and you can see that only at Z minus 12, there is a clear signal for gadolinium, while for the other positions, you still see the 2.2 MeV. This is an efficiency effect from this 2.2 MeV gamma. So we can also see the capture time distribution at Z minus 12. This time constant is about 130 microseconds. This is roughly what we expect at these kind of concentrations, although again, the concentration is not yet that homogeneous to really compare to Monte Carlo yet. Now we have other sources of neutrons. Spallation neutrons is another one. We have in Super K a cosmic ray immune rate of about 2 Hertz. So we expect spallation about 10,000 spallation neutrons per day. So we can look for neutron candidates near the parent muon in the lower half of the detector. Here I am comparing runs before injecting gadolinium and runs after injecting gadolinium. Again, you see very clear in the energy spectrum, the 2.2 MeV gammas, and then very clear the captures on gadolinium. Again, the capture time, very clear, similar results as with the previous analysis, 136 or so microseconds. Very nice in this analysis is that we can look at neutron multiplicity, comparing pre-GD and now GD runs. We can see that we do not only see more neutrons, but also very high, we're able to see very high neutron multiplicities. I think this is really nice to see because it allows many improvements in many studies. So you can see here in this study these neutron capture candidates, how we can see them more and more in upper regions of the detector approaching the center part of the detector as the time goes by and we have more and more gadolinium in SK. finally stopping muons captured on oxygen. Finally, they may eject one neutron, again being captured on gadolinium. If we look at the lowest part of the inner detector, we can very quickly see how this is happening in very early days of the injection, not yet in the upper regions, but sure enough, at some point, we see them too in higher and higher regions of the detector, and we expect to continue to do so in the next days. So with this, just the loading schedule. We are right now here almost in August, still diluting and injecting gadolinium. We will finish by middle of August. Then it will come a commissioning phase, and afterwards some calibrations just in time for possible T2K physics runs at the beginning of 2021. Let me summarize very quickly. Neutron tagging is very useful, as Sonia and other speakers before has Volodymyr too has been shown. It's safe, as we have shown also in EGATS. The tank has been refurbished. We have been starting injecting gadolinium from July 14th. We will finish around middle of August. We have seen gadolinium already in the detector, not only directly from samplings, directly from the inner of the detector, but also looking at neutron captures from different neutron sources. So yeah, exciting physics days ahead with neutron tagging at Super KGD. Stay tuned. That's all. Thank you.
Thank you very much. So questions? Okay, we have audience raise a hand. Let me see. Is it Marcos? Oh, who is raising the hand? Somehow doesn't. Okay, Sunny. Okay, Sunny.
Yeah, yes.
I think you can.
Yes. Okay. So congratulations. It's really nice to see this neutron capture on gadolinium. And my question is, you show this, the neutron capture on gadolinium and hydrogen, the spectrum. If you can go back that slide.
You mean
yes, here, yeah. So I see the, so gadolinium capture case is supposed to be around 8 MeV, and hydrogen capture should be 2.2 MeV, but it doesn't seem to match. It's because calibration.
Only apparently. It's very, very easy to understand. As you say, the gamma casket is 8 MeV integrated, but then this has to be converted into an electron, right? Going into the running into the SK tank and quantum scattering. So that's basically 4.5 MeV. That converts into 4.5 MeV.
Okay. And for 2.2 MeV case, it becomes around 3 MeV.
Yeah, no, the thing here is that we are not 100% efficient on 2.2 MeV. So this would actually go up. This is an efficiency artifact, so to say.
Okay. That's inefficiency.
Yeah.
Because you...
That then I think with...
Because your energy threshold is not really close to MeV.
Right. This is actually a specific DAQ that it's trying to push. Actually, it pushes the efficiencies as low as we can in Super K, but it's not yet. I mean, it's not as efficient as we would like in 2.2 for 2.2 MeV gammas.
Okay. Anyway, congratulations.
That's and where we want gadolinium, right? So we have a clear signal at high energies that we can, where we have much higher efficiencies to detect.
Okay. And your ultimate goal is to have a 0.2% loading, right?
Yeah. I'm afraid you will ask me when.
When it will be?
I think this depends on many factors. They are not definitely not my control, and I cannot really answer to this question, I'm afraid.
Okay, thank you.
Okay, thank you. I think we're running out of time. There is one question in the question and answer, so I would suggest Luis to go ahead and take a look. So we're gonna go to next talk. So we come to the last talk of this session, the sensitivity study for astrophysical neutrinos at hyperchemically from Dr. Takatomi Yano. Thank you.
Yeah, I think you can see my slide.
Yes, I can see your slide.
Thank you. Yeah, I'm Takatomi Yano from University of Tokyo for hyperchemical collaboration. So I will talk about the sensitivity study for astrophysics neutrinos at hyperchemical. So at first, the hyperchemical project is next generation large water Cherenkov detector. And Hyper-K will be constructed at GIF prefecture in Japan. Yeah, the detector size will be about 8 times larger than superchemical, and the fiducial volume size will be 9 times larger than that. And we have improved photosensors, so the photo detection efficiency is about twice of that was used for superchemical. So yeah, let me say we will have twice of photoelectrons comparing to SK at same energy. And Japanese budget is approved at 2020. And yeah, we plan to start our observation at 2027. And so yeah, basically the detector structure and the detection method of neutrinos is quite similar. I mean, actually identical with superchemical. So yeah, we will use Cherenkov light, and yeah, I'm showing some event display that's coming from simulation. So for unject muons and 10 MeV electrons. And yeah, the property of neutrinos could be measured with charge lepton generated by reactions in ultra pure water, and the energy position, direction, and particle ID can be done. And the point is real-time and event-by-event analysis is possible with our detector. And yeah, for astrophysics neutrinos, here I will mention about the solar neutrinos and the supernova neutrinos and the supernova relic neutrinos. And yeah, for the purpose of solar neutrinos, there is confirm the burning process or modeling of the sun, and yeah, check the property of neutrinos, I mean neutrino oscillation. And for supernova neutrinos, yeah, we can examine the supernova explosion mechanism, and we can work as the supernova monitor, or yeah, it may be possible to examine the nucleosynthesis scenarios. And yeah, for supernova relic neutrino, yeah, also for supernova explosion mechanism or and star formation rate and extraordinary supernovae like a black hole formation. So, and of course we have another astrophysical neutrinos, for example, dark matter annihilation or following up measurement with gamma ray burst or gravity wave measurement. But yeah, I will mention about low energy part in this slide. And for solar neutrinos, yeah, there was several good slides in this session. Yeah, basically sun is burning with nuclear fission reaction, fusion reaction, I mean PP chain or CNO cycle. And yeah, the neutrinos is the only neutrino can bring out the information of today's status of solar core. And with hyperchemical, yeah, the target energy threshold is, let me say, above 4.5 MeV in our visible energy. So yeah, but still, yeah, with this energy threshold, our main target will be boron 8 neutrino. and we expect 130 neutrino events per day. Yeah. And with this large statistics, we can perform solar neutrino studies. So yeah, solar neutrino is important in particle physics and also for astrophysics. And the first thing will be the first thing in particle physics will be the precise measurement of delta m square. So that's day-night asymmetry and also supernova neutrino spectrum upturn. So that's related to non-standard interaction. So that was mentioned previously. And also, as the astrophysics topics, so discovery of ICHEP neutrino or variation of supernova neutrino flux yeah, will be important. So yeah, right up a figure I'm showing the super K result of the yearly neutrino variation and yeah, sunspot numbers. Yeah, we can perform this kind of analysis with more statistics. And yeah, non-zero day-night asymmetry of solar neutrino caused by terrestrial matter effect is indicated by super K. And the day-night asymmetry leaves smaller delta m square value in solar neutrino analysis comparing to the reactor neutrino analysis. So for the day-night, so with hyperkamiokande statistics, we can separate the solar-best delta m square value and the Cameron diamond reactor best value above 4 sigma with 10 years measurement and assuming 0.3 systematic errors. So, and we can also perform CPT violation test or difference, check the difference between let's say neutrino and anti-neutrino. Sorry. Yeah, we can perform CPT violation test by looking at the difference between neutrino oscillation and anti-neutrino oscillation. And precise delta m square 2-1 measurement also contribute to CPV test, violation test in hyper-K long baselines. And in bottom figure, I'm showing the super K result at 2019. And yeah, but it will change after over 20 years measurement. So we can separate, after 20 years, we can separate them by 5 sigma. But as you already know, so recently, Super Kamiokande updated their oscillation results. And the tension between SK plus snow and Cameron best, the tension was reduced to 1.4 sigma from 2 sigma. So yeah, for new super K delta m square value, the hyper K sensitivity of separation study is ongoing. And yeah, left bottom figure is showing the what to say, our observation period and also sensitivity to the delta m square separation between solar based and so reactor based. And the other solar neutrino topics is, one is the ICHEP process neutrino. So yeah, this is undiscovered solar neutrino because of its small branching ratio. So yeah, we hope hyper-K large statistics will work on that. And yeah, and we hope to test the solar models. The sensitivity will be 1.8 to 3 sigma after 10 years. So yeah. And also, there is another topic, energy spectrum upturn. So that's the verification of the neutrino oscillation. Yeah, that's also correlated with the delta m square measurement. So, or to search the new physics beyond the standard model. So, non-standard interaction or sterile neutrinos. So, yeah, we can separate the scenario with upturn or without upturn with, let me say, 3 sigma after 10 years measurement. Okay. And so, yeah, next topic is supernova neutrino. So, yeah, 4 collapse supernova neutrino emits all kind of neutrinos, and 11 neutrino events were observed by Kamiokande from supernova 1987. So, yeah, we expect 15 to 80,000 events in hyper-K from supernovae at 10 kPa. And yeah, our physics motivation is examine the explosion mechanism of such a supernovae or proto-neutron star formation or black hole formation. And of course, we can perform kind of neutrino physics like mass hierarchy. And yeah, we can perform, we can contribute to multi-messenger measurement with gravitational wave, gamma ray, X-ray, yeah, that kind of measurements. And yeah, let me talk a bit more detail. So yeah, for supernova neutrino observation, we can provide precise supernova neutrino time profile and energy spectrum measurement. And based on this result, we one of our members performed the supernova model discrimination study. So yeah, model discrimination between 5 supernova models recently studied and presented at the Neutrino 2020. So I took a table from his poster, and with 300 events, so that's corresponded to 6 to 100 kiloparsec, we can identify these models above 97%. So yeah, we believe that's quite what to say, variable input for theorists, and we can cut down, or we can what to say, we can spot some area of theoretical available sorry, anyway, we can provide important information for theorists. And also, with the large volume, we think we can prove dim supernovae or black hole formation at nearby galaxy by using neutrino observation. So I mean, so if black hole formation is happened, we will see large neutrino flux at first, but it will be suddenly dropped after the black hole formation. Yeah. And so that's for supernova. And I would like to make last comment about supernova relic neutrino with hyper-Kamiokande. So yeah, it's also already mentioned. So yeah, relic neutrino, supernova relic neutrino is diffused neutrino coming from all past supernovae, and not discovered but promising extragalactic neutrino source. And yeah, our motivation is test the star formation rate by detecting the supernova relic neutrino. Yeah, there is factor 2 discrepancy between rates of what to say, the rates of formation and the number of supernovae. Yeah, so we can contribute to resolve that discrepancy. And yeah, we can deconvolute the energy spectrum of supernova burst neutrinos. So that corresponds to temperature inside the supernova neutrinos. And also, as I said, we can see the contribution of extraordinary supernovae, so black hole formation of dim supernova in supernova relic neutrinos. So in left upper figure, I'm showing the two examples of relic neutrino model. with different neutrino temperature. So if we have black hole,
it's about 2 minutes left.
Okay. Sorry. Okay. Anyway, if we have black hole formation, the energy will be a bit higher. And yeah, we can observe the supernova neutrino events in 70 plus minus 12 events by in 10 years, and it will be about 4 sigma for relic neutrino signal sensitivity. Okay, so finally, this is the summary. And sorry, I don't have enough time to say for this summary. So please just read it.
Thank you very much. I think we already occupied the coffee break time. Just one quick question, if there's any. If not, I think I would encourage you to do the Mattermost channel to exchange ideas and ask questions for discussions. And I would like to thank all the speakers for their nice talk. And this will then conclude this session. So thank you very much. Thank you all thank you. Oh, the next session will be in, I think, 6 minutes.
Hi, can you hear me okay? I'm the next chair.
Yes, I can hear you. I'm about to leave as the chair, so.
Okay, thank you very much.
Thank you. Sorry, I occupied the coffee break.
Yeah, it's a coffee break. Do any of the speakers for the next session want to test their presentations, or has everyone done that already?
No, if it's possible, it would be nice. I do.
Okay. Hi. Is that Konstantin?
Yeah, it's me.
Okay. So, are you able to? Do I need to do anything? Yeah. Go ahead.
Yeah, I can try.
Okay.
So I can. No. Yeah. Okay. Can you see my screen?
I can see your video, Konstantin, but not your screen.
Strange. Oh yeah, one moment. Like this. Now you see.
Yeah, that's good. Do you want to try going to full screen?
Yeah.
Perfect.
Okay, you see everything, yeah? And you hear me well?
Yep, sounds perfect.
Okay, let me just check. Okay, everything is visible. Okay, thank you. I'm ready now.
Great, thank you. Okay. Does anyone else want to test their presentation?
Hi, David. I would also like to test it if
Go
possible.
ahead. Looks good. I can see the slide in full screen.
Okay, very good. Thanks.
Okay, great. Perfect. Okay, so welcome everybody to the second part of today's neutrino parallel session. So this time we still are covering a variety of topics, starting with ICECUBE and Dune, and then we're going to hear a lot more about neutrino mass determinations directly and also through some very recent and interesting neutrinoless double beta decay results. So we have more than 50 people currently in the session. So I suggest we go ahead and start. And the first speaker talking about constraining dark matter neutrino interactions with ICECUBE data is Jungkook Kim. Can you start your screen share?
Okay, thank you. Okay, can you hear me?
Yep, we can hear you and see your screen, so go ahead.
Okay. Okay. Thank you for introduction. Hello, I'm Jungkook Kim. Today, I'm going to talk about new dark matter neutrino scattering bound. So by using the ICECUBE recent event, I obtained the new constraint on the dark matter neutrino scatterings. So in this work, I collaborate with Professor Ki-young Choi and Professor Carson Lo. So this is contents of my talk. First, I will talk about what is the ICECUBE 700922A event, and I will talk about how to get a new constraint on dark matter neutrino scatterings, and I'll briefly review what is non-constraint on constraints. And as an example, I will consider the complex scalar dark matter models and find some scattering, search for the scattering behavior and conclude my talk. First, almost 3 years ago, ICECUBE collaboration detected 300 TeV neutrino event. And thanks to the ICECUBE neutrino alert system, the other experiments such as Perimlat, MAGIC, and SWIP, and so on, they detect the gamma ray signals. So that and the gamma ray signal from the direction of neutrino propagations. So this event is identified with the flaring blazar, which called this. And thanks to the neutrino gamma ray, both neutrino and gamma ray observations, we can find some distance from the source to the Earth. The distance is 1.4 gigaparsecs. And taking into account equatorial coordinate system, we can describe the source into the two angles. One is light as ascension is 77 degree and declination is 5.7 degree. And from this information, which physical quantity can we calculate it? So that is our question. So we consider the mean prepass for a neutrino, and the definition of mean prepass is given by this. So mean prepass is inversely proportional to the number density and scattering cross sections. So okay. So if there exists the neutrino and interaction between neutrino and dark matter, then mean prepass can be awesome. We can evaluate the mean prepass of neutrinos. So we will consider this one. And thanks to the interactions of neutrinos with the dark matter can suppress the original flux of neutrino coming from the blazars. And this is so this pi node is the unknown vector. So we will focus on these exponential suppression vectors. And the given neutrino energy, then scattering cross-section becomes constant. So only important information is dark matter number density along the path. And taking into account the 90% suppression of original flux, then the integration of cross-section times dark matter number density is less than 2.3. That is our constraint. So to change the code to get the number density along following the neutrino propagation, we have to change the coordinate from equatorial coordinate to the galactic coordinate. So from the galactic coordinate, the angle, it is also described the two angles, L and B. So L is 15.4 degrees, so along this direction, and B is minus 19.6 degrees, so these directions. So neutrino propagation, neutrino does not travel through the galactic center. This means we can choose any dark matter profile. This because the dark matter profile have there is the deviation along inside the galactic center, but the neutrino propagation is all dark matter profile is same, behavior is same, so we can choose any dark matter profile. And the suppression factor can be divided into the two contributions. The first one comes from the cosmological dark matter. This is the outside of the galaxy. So we don't know the information about the outside of galaxy. So we take the average dark matter density, which determined by the Planck 2018 data. The energy density is given by this. And we obtain 10 to 22 GeV per centimeter squares. And the other one comes from the galactic dark matter. So as I said before, we have any dark matter profile. We can choose any dark matter profile since there is no dark matter profile dependence. But I take NFW dark matter profile and calculate the integration of the total number of dark matter density, and we got the 10 to 12 2 GeV per centimeter square. Accidentally, both contributions from cosmological dark matter and Milky Way dark matter are very comparable. This is because very small cosmological dark matter is compensated by the long distance from the source. And so identification of the source can allow the precise evaluation of neutrino flux change due to dark matter neutrino scattering cross sections. So this is our main result. So cross section over the dark matter mass is less than 5 times 10 to minus 23 centimeter square over GeV when neutrino energy around 300 TeV. This is our main result. And now let's review the known constraints. First constraint comes from originates from the Lyman alpha. So if dark matter stay in thermal equilibrium, then for a longer time due to some elastic scattering process, then this phenomenon might suppress metal perturbation and reduce the amount of small-scale structure today. So to avoid these problems, the elastic scattering should less than these values. there is the two scattering bound. One is the constant cross sections. The other one is the temperature dependent cross section. But here, this constraint only can be applied for the deuterium energy at around 100 electron volt. So we put it here 100 electron volt, and T0 is the current temperature of the universe. So this vector is 10 to 6. Then this constant cross section and T dependent cross section is the same order at temperature when universe temperature around 100 electron volt. So this constant is same at 100 electron volt. Then another one is the other constraint comes from the supernova explosions. Supernova is the first multi-messenger observation. So when super Kamiokande detected neutrino coming from the supernova with the 10 MeV, and we can obtain the distance. So thanks to the fixed direction and energy, we can neutrino dark matter interaction can also constrain. So this is the current is known observation values here. So in the neutrino energy and elastic scattering cross-section regions, there is a three upper bounds. So if we consider simple power law cross-sections like this, given by this, then if in the case of n equals 0 case, the Lyman alpha provides a stringent constraint. But if in other case, for example, n equals 2 or 4 case, the new constraint obtained by our study, this cross-section, this bound can provide a strong bound. That is our point here. Then now let's embed our bounds into the complex scalar dark matter models, and the relevant interaction Lagrangian is given by this. Chi is the dark matter, scalar dark matter, and N is the mediator, and UL is active neutrinos. So here, as inputs, I took the dark matter mass equal to 1 kb, and depending on the mediator mass, the behavior is changed like this. So so let me conclude my talk. So identifying source of astrophysical neutrinos give us the additional information. So by using this information, we found some new constraint on dark matter neutrino scattering is given by this when the neutrino energy equal 290 TeV. So some certain class of new physics dark matter models can be proved by the or some constraint by these new values. So thank you for listening.
Thank you very much. Thank you.
Thank you.
Thank you. Do we have any questions for the speaker? Maybe I can ask a quick question if that's okay. One piece of your argument I didn't fully understand is how do you know that the flux is suppressed by at most 90%?
This actually this original flux is pi naught is unknown, but we observe the dark neutrinos from ICECUBE. So this is pi is the neutrino flux, expected neutrino flux from ICECUBE, and there is the exponential suppression factors. So exponential, so 90% suppression, which means the exponential minus 2.3.
But how do you know that the initial flux, how do you know that phi 0 is not much larger than we think? And so the suppression could also be much larger to give this.
Yes, there is some, might be some, okay. But we do not know, we don't know much about the flaring blazars. So we just assume the pi naught might be the some is almost same with the pi 0, or there is some suppression. So I just consider focus on this one, some like some 2 sigma constraints.
Okay. Okay. All right. Thanks very much.
Thank you.
Thank you. I think we better move on to the next speaker in the interest of time. So, Seb, are you ready to share your screen?
Yep, I will go ahead.
Okay, so Seb Jones is going to talk about the June physics program. Go ahead, Seb.
Okay, so yeah, thank you very much. I'm going to give an overview today of the June experimental physics program. So, Dune is the deep underground neutrino experiment. It consists of a broadband neutrino beam, which is sent from Fermilab in Illinois to the Sanford Underground Research Facility in South Dakota, which is a baseline of 1,300 kilometers. I've included a kind of helpful diagram here at the bottom. So the beam is produced at Fermilab, where it's initially measured in a multi-component near detector, which includes a liquid argon component. It then propagates through the Earth before being measured again with some of the neutrinos having oscillated in a liquid argon far detector, which will have an eventual 68 kiloton mass. The far detector is located 1,500 meters underground at surf to reduce cosmogenic backgrounds. It consists of 4 individual modules, each with a total mass of 17 kilotons. That's equates to a fiducial mass of 10 kilotons per module. Diagram on the right shows the position of 2 of these modules in red inside the caverns. The first of these modules will be a single phase liquid argon TPC. And for the further modules, the collaboration is currently developing both single phase and dual phase LAR TPC options. So the beam, as I mentioned, it's mainly muon neutrinos. So the plot on the left shows the flux at the near detector when running in neutrino enhanced mode, or mainly muon antineutrinos when running in antineutrino enhanced mode. And then this beam is measured in the multi-component near detector. I've got a diagram here of that. It sits 574 meters downstream of the beam, light neutrino beam production target. It consists of both a liquid and gaseous argon component and a beam monitor. And the primary purpose of this near detector is to allow the characterization of the neutrino beam, as well as constraining cross-section uncertainties. So what does the June physics program consist of? Today, I'm mainly going to be talking about the long baseline neutrino oscillation physics. June wants to make a measurement of this CP violating phase of the PNS matrix, delta CP, and potentially this could lead to evidence for discovery of CP violation by neutrinos. Dune is also expected to determine the neutrino mass hierarchy, and furthermore, it can also measure, it'll also have sensitivities to other elements of the PNS matrix, notably the mixing angles theta 2,3 and theta 1,3. Dune is also expected to be sensitive to neutrinos from core collapse supernovae. And there are also a whole host of BSM processes that Dune will be able to search for, including nucleon decay and neutron to antineutron oscillation. So there are some talks here at ICHEP that I have provided the names of. So start off talking about our long baseline sensitivities. Our far detector samples are shown here. And for our far detector samples, a full simulation and reconstruction was used, including a convolutional neural network for identifying the neutrino flavor, of which there is a paper out now which details this. The upper two plots show the disappearance measurement, so that's the particles identified as muon neutrinos or antineutrinos, and the lower two plots show the appearance measurement, so the expected event rates for electron neutrinos and antineutrinos. In the lower two plots, the varying lines are just the change in expected event rates for different values of delta CP. The sensitivities I show in this talk were determined using a 4-component fit of the far detector data along with a constraint from the near detector. A full suite of systematics was used, and this has now been published. It's available on the archive, a paper detailing this analysis in further detail. For our Asimov fits, the new fit 4.0 best fit points were used as the oscillation parameters. One quite big advance with this analysis was our very thorough implementation of the systematics. Our flux systematics were determined by varying both models of hadron production in the beamline, as well as and other certain design parameters of the beamline, such as the magnetic Horn currents and other parameters such as that. On the neutrino interaction side of things, both reweighting parameters built into our neutrino interaction generator, Genie, were used, as well as custom weightings developed for this analysis, which were sometimes drawn from work that has previously been done in other long baseline oscillation experiments. Finally, for our detector systematics, uncertainties on the detector, the energy scale for various particle types were developed. And what this very busy plot on the right just shows is this is the post-fit constraints on all the various systematics that we used in this analysis. And you can see that some things that we expect to be well constrained by the near detector, which are the green bars, such as our flux parameters. You can see that, as we expect, they're well constrained. And then there are other parameters, such as our far detector systematics, which are not well constrained by our near detector. So these two plots show the CP violation sensitivity as a function of the true value of delta CP, left for true normal ordering and the right for true inverted ordering. The bands here represent 1 sigma variations in statistics, systematic and oscillation parameter throws. The lines are just the median of these throws. And what you can see here is that after 10 years, so the orange band of staged running, there is a significant CP violation discovery potential across true values of delta CP, and for both hierarchies, you can see that these lines move beyond this sigma equals 5 dotted line. So here we look at the CP sensitivity over time. The lighter blue line shows that after 10 years of running, discovery potential is reached for 50% of true delta CP values. The difference between these two lines, the dotted line and the solid line here, is just with and without an external theta 1,3 constraint applied. And after 15 years of running, the evidence of CPV the evidence threshold for CP violation is reached for 75% of delta CP values. That's this lower blue line here. This is our delta CP resolution as a function of delta. And looking at the orange band, you can see that after 10 years of staged running, the delta CP resolution varies between 10 and 20 degrees, depending on the true value of delta CP. And then moving to our longer exposures of 15 years, you can see that at the most favorable point, so the CP conserving values, the resolution drops down to around a 7 degree kind of mark. here we can see that Dune is very, very sensitive to the neutrino mass hierarchy. This shows the sensitivity to the mass hierarchy. So what these blue lines are showing you is that Dune will obtain a definitive answer for the mass hierarchy within 7 years, regardless of the values of the other oscillation parameters. And here you can just see how quickly that Dune will reach that result. The lower blue line here, lower blue band, I should say, shows that after 2 years, for all values of delta CP, the mass ordering is measured to 5 sigma. I also mentioned that Dune will make precision measurements of theta 2.3 and theta 1.3. In both of these plots, the current constraints, the current 90% confidence limits on the oscillation parameters are shown in yellow. And the left-hand plot shows that after 7 years, Dune will have already made a great improvement on these limits on the value of theta 2.3. And over on the right-hand plot, you can see after 15 staged years of running, Dune's theta 1.3 measurement will be comparable with reactor experiments. That's this. You can see that this green line here shrinks to around the size of the yellow area. Dune will also be sensitive to supernova neutrino bursts. So these are primarily through galactic core collapse supernovae, and in particular the electron neutrino flux. Via the production of an electron in the detector. Not only can this provide information about the physics of supernova core collapse, but it could also give some hints about the oscillation physics. This upper plot shows the time profile of events within the detector from a supernova, core collapse supernova. And you can see that in this neutronization section, there is a significant difference in the time profile between where the neutrino mass hierarchy is normal or inverted. So that's the red and the green lines, or the green and the red lines. And finally, Dune will also have sensitivity to beyond the standard, a wide range of beyond the standard model physics programs. Its large far detector mass allows searches for proton decay, and in particular, the decay channel of a proton to a K plus and an antineutrino. On the right, I just have a simulated event display of an event, of just such an event. And this was actually selected by the automated classification for this particular study. Additionally, Dune's very long baseline means that non-standard matter effects may be visible in the far detector due to the very long baseline. And these are just two of many, many BSM searches that be able to be searched for in Dune. So in summary, Dune will enable an exciting physics program, including the measurement of possible CP violation in the lepton sector, determination of the mass hierarchy, precision measurements of other oscillation parameters, as well as supernova neutrinos and many BSM searches. The far detector TDR Volume 2 contains many more details on the physics possibilities, and there are a series of publications either available or planned which are made up of parts of this volume of the TDR. And finally, I would like to encourage you all to go out and listen to some of the 22 other Dune talks at ICHEP this year. Thank you very much for listening.
Thank you very much, Seb. There is a question from Thomas. Thomas, do you want to ask your question?
Yeah, I can ask the question. So thanks, Seb, for the talk. Just one question. Could you be more specific on what is meant by your custom weighting of Gini interaction models based on what was done for longer baseline experiments? Like, I think you don't have any data you tune to, but what is actually you do with tuning the Gini interaction?
So for Gini, there are a number of, built into Gini, there are a number of tunes that cover discrepancies due to tuning on different data. So they were used. And then there were also, I think, weights developed for the NOVA experiment based on some of the cross-section physics that they observed that were integrated into this analysis.
Yeah, okay, thank you.
Okay, thanks, Seb. Any other quick questions for Seb? Okay, I don't see any, so I think that's a good segue to the next talk, which is by Mateus Carneiro. Now, I understand this is going to be a recording.
Yes, I'll share the screen and start the movie. Can you see the start of the movie?
Yeah, we can see that.
Okay.
Hi everyone, I'm Mateus Carneiro. I'm here to talk about neutrino interaction physics and the Dune near detector. Thank you very much to the organization for the opportunity. So let's jump right into it. I think the main point that I want to convey here is that knowledge of neutrino nucleus scattering cross-sections is crucial to the global neutrino physics program. Why? Well, although maybe we understand what happens when the neutrino interact with a single stationary particle, like in this example here, that you have a neutrino interacting with a proton producing a charged ion, and a lepton and a neutron, we actually don't really have full understanding of what happened with these particles inside the nucleus. There are final state interactions and other different nuclear effects that can make this one charged ion created showed up as a pi zero. It maybe just undergo elastic scattering and change the momentum information. It can be absorbed and be seen in your detector. So we need to always keep in mind that this particle that was created didn't really walk it all the way free into your detector. What you really have is this somewhat black box where you have a neutrino interaction. You may see the lepton here, but you have these particles coming out, and you actually need to identify them and then try to understand what happened. And we also need to remember that most detectors are made with heavy nuclei, so it's really important for us to understand this. To try to be more quantitative, if you think about how these detectors actually extract oscillation parameters, there is a interaction of interaction models and neutrino energy reconstruction. Once that happens, you actually have these nuclear models affecting your event rate, which is the main thing that is used for oscillation, right? Just putting here a quote from the NOVA collaboration, after a constraint from the ND is applied, so after the constraints that having a near and far detector are applied, cross-section uncertainties currently comprise 30 to 50% of the systematic budget. So it is a really big effect, and we need to address it. Another example here is that I'm showing you in two different ways the new appearance expected in the Dune far detector. What you see in this plot here with the dotted lines, it are actually the expectations for different values of delta CP, and what you see here is the size of the systematics we have. It's not hard to see that the size of the systematics we have now may actually be a problem for the measurements we plan to do. And this is not just true for Dune and NOVA, but it's actually true for every oscillation experiment. Trying to be more specific, let me try to convey how this gets into something like CP violation sensitivity. So what I'm showing here is the CP violation sensitivities for the Dune far detector, well, for the Dune as a whole, for different cases. The point is that to convey all of this, we need to use event generators in Monte Carlo. But what if the models that are included on it are not perfect? Well, first of all, we have this line here that shows you the sensitivity using Gini, which is our primary neutrino event generator, right? And in this study, we're just using that as if it was a perfect model. And this is the sensitivity we achieve. But if we use a different but plausible model that is usually implemented in a different event generator, and then we put this into our simulation as fake data, that generates a difference, and actually that needs to be taken into account as a systematic error. Once with that systematic, you try to reevaluate the violation for the sensitivity for CP violation. This is the sensitivity you achieve. So you can see by just using one different model or considering one different model, the sensitivity actually goes down from 5 sigma. Well, and if you think about this a little bit more, there are not just 2 models out there. There are actually several different models. And not just that, there are different combinations of them and different implementations of them. So this, once you take this into account, you actually reduce the sensitivity even further. Okay, so how can we try to do this? Let me introduce you to the Dune near detector complex. The Dune near detector complex is formed by 3 subsystems. You have the ND-LAR, which is a modular pixelated liquid argon TPC. It's a primary target because in here the beam's coming from right to left. And it's the one that's most similar to the Dune FAR detector because of liquid argon. Then you have the ND-GAR, which is a high pressure gaseous argon TPC. It is surrounded by an ECOL and a magnet. It is a phenomenal muon spectrometer, and because it have a nice particle identification and low energy threshold, it can also be used for constrained nuclear interaction models, which we're going to talk about in a second. And then we have the SAM detector, that is a tracker surrounded by ECOL and a magnet. And the main goal is to have on-axis monitor of the beam spectrum. Why specifically on-axis? Because both of the dispersed detectors, they can actually move up and down in this direction. So they can take data in different off-axis points and what we call Dune prism. I don't have a lot of time to actually talk about this, but if you are interested, there's a talk by Patrick Dune on the status of the Dune near detector with way more details than this. Okay, so how can we try to use these detectors to separate interaction channels? Well, first of all, what I'm showing you here is the spectrum of neutrino cross-sections per neutrino energy. And I'm showing what you usually see when you talk about neutrino interaction, that you have these different channels, right? Like quasi-elastic, versus pion production, deep inelastic scattering. The points that I said earlier, these map the initial interaction of the neutrino in the nucleus, but they do not really map to what you see in your final detector. What you see here, are the events expected in the gaseous argon detector per pion multiplicity. So the point is that there's not really a mapping, I apologize. There's not really a mapping between different multiplicities here to the actual interaction channels. So how can we use that to convey and look into the models? Well, we have several different tools, but the first thing you need to do is to actually identify these particles. And this is one thing that we have really good identification on both the gaseous and the liquid argon detectors. What I'm showing here is the final confusion matrix for the gaseous argon detector, where you have the reconstructed different multiplicities and the true different multiplicity. And you can see that we have a really good efficiency on this. You actually should keep in mind that this is also done with preliminary simulation. We expect to have even better efficiencies once we get to new and different techniques that we can implement here. Another thing that's really powerful for us is the statistics, right? Sorry, this is a lot of information, but just to point, these are events per year in both the liquid detector and the gaseous detector. And just to give an idea, the most recent Minerva high statistics sample have 16 to the 5 events, while with 2 to 3 years of data taking, while these are something that we can take in most channels here with less than a year. So this is also really important to achieve something. So, but how can we really address the model differences and those different bias? What I'm showing you here is the comparison between the expected events per different pion multiplicity in the final state for the Q square and GeV square in the gaseous detector. This comparison that I'm doing, this ratio that you're seeing, is between Neuro and Gini. Neuro and Gini are 2 different neutrino event generators, and they both have different models implemented on them. And it's not hard to see that there is a big difference in expectations of the final state events that we can have. And actually what I'm showing here is both the truth and the reconstructed, because this effect, right, the reconstruction itself also makes a big difference in here. And the point here is that if we have this power of comparing all of these different models with high statistics, enough to actually separate all the channels, and then we can compare that with data, this is a really good insight, so we can select, optimize, and tune models working together with theory and community and the generator developers to have a higher precision in the future, not just for Dune, but for the community as a whole. A different technique that we can use, it's what we call the transverse kinematic imbalance. It's a newish technique, so let me try to explain for a second. First, imagine the neutrino interacting with a stationary nucleon target. So you have the neutrino momentum interacting with this nucleon target, and then you have the final momentum, and what you see here is just the transverse component of it. In this case, it's obvious that you would have a balance, right? You would have consistency between initial and final momentum, but what we really have, it's this target being inside the nucleus. The point is that you can put together smart variables that can tell you not just the initial momentum of the particle that was hit by the neutrino, but also the effects of the final state particles, because they are the ones that gave you this imbalance between momentums. This is a technique that was used in both Minerva and TK with really good agreement with the current implemented models, but not really in the transition between different nuclear models that we see. So data doesn't really agree in certain parts. So the whole point here is to try to use this in Argon, because this would give us a really good insight into not just the different interactions that we can have, but in the A dependence. One thing that we don't really have much is data of neutrino cross-sections in Argon, and having this measure can be really important. And you can see the difference here. Well, of course, it's not just the same energy, it's not really the same energy, but you also have different targets, and you can see the difference. Like Dune would give us really good access to 2p2h interactions, also DIS interactions, and this is really important for us to look at. Okay, well, thank you very much. I hope you understand that neutrino nucleus cross-sections is really necessary for oscillation experiments and for neutrino experiments as a whole. The Dune detector not only provides the near-field detector ratio to constrain the flux and uncertainty, right? It's usually the main reason to have the near detector, but it also can measure cross-sections and constrain the different interaction models using Argon and in the exact same beam as the far detector, which also give us consistency to take both neutrino and anti-neutrino data, which is also something really important to understand in the cross-section point of view. The Dune near detector CDR will be publicly available soon with way more details than this, so please stay tuned. Thank you very much.
Okay, I don't think the speaker is with us online. So what I suggest is that if people have questions addressed to that talk, that they type them in Q&A, and the speaker may be online later to address them directly. Okay, so I think we should move on, and the next speaker is going to talk about tau neutrino production at SBS and the NA65 experiment. Svetlana, are you ready to share your screen?
Yes. Can you see my screen?
Yep, that looks good. It's in full screen, so go ahead.
Thank you. Thank you for introduction. So I'm glad to have a possibility to tell you about DS tau experiment, which studied tau neutrino production at CERN SPS. So at the moment, tau neutrino is one of the least studied particles. There are only few measurements. Only donut experiment observed tau neutrinos in direct beam, and there are several experiments which registered tau neutrinos from oscillations. And at the moment, cross-section error is more than 50%, which mainly caused by systematic uncertainty in tau neutrino production. And another interesting topic that LHCb reported a hint on lepton universality violation from beta decay. So a precise measurement of tau cross-section would provide information to test lepton universality in a neutrino sector. If we have a look on the scheme of experiment, which measure tau neutrino cross-section with accelerator, we can see that the main source of tau neutrinos is this decay, ds to tau, when a couple of neutrinos are produced, which appears in interaction of high energy protons. And as you can understand from our experiment name, this is our main subject of interest. So the goals of our experiment is, first of all, study of tau neutrino production for future tau neutrino experiments, which include first measurement of ds double differential production cross-section, and will provide tau neutrino production at the range of 10 GeV with the beam dump method. And this allowed to reduce uncertainty on tau neutrino flux from more than 50% to 10%. And also charm physics is interesting itself. For example, study of intrinsic charm component in the proton. As I said, we're aiming to detect such events. And this is quite challenging because the length of such topology is just a few millimeters. And here you can see the kink between ds and tau. It's about just few milliradian. And detection of this topology is, can be done using emulsion detector with high spatial resolution. This how our detector module looks like. It made of 10 basic units. Each unit is a target, for example, tungsten plate, followed by 10 emulsion films interleaved with the plastic layers. And here on the picture, you can see the exposure of such a model. Its size of 10 by 12 by 8.6 centimeters. And yeah, actually this model also have a so-called emulsion cloud chamber in the downstream part to measure momentum of interaction production products. So if we keep to use this size of models, in the experiment, we have to expose and analyze 370 models to achieve our goals. During exposure, model moved with the target mover with respect to the beam position. And also we have detectors to monitor beam profile and beam intensity. So as I said, we're looking for such signals where double kink from ds tau decays accompanied with a charm decay charged or neutral. The detection efficiency is estimated with the PFA. It's about 20%. And the main background to this signal comes from secondary hadrons interactions. Usually there are nuclear fragments in the interaction vertices, but if there are no registered nuclear fragments, it's our background. So for full statistics, we expect about 1,000 signal events and about 18 background events. So at the moment, we already perform a feasibility study, test beam, and pilot run. Now we are in the middle of analysis of pilot run data. It's about 10% of the full-scale experiment, which already, after analysis complete, will give a possibility to reduce uncertainty on the flux up to 30%, to revise donut results, and to perform some study in charm physics. And we are preparing to physics runs, which will be in the next 2 years, 2 weeks each. So we're planning to use 2 targets, tungsten and molybdenum, and to collect about 500 signal events in each target. And in some experiment, we'll use about 600 square meters of emulsion. So for pilot run, we produce emulsion manually at Nagoya and Bern facilities with a speed of about 7 square meters per week. But for physics run, the amount of emulsion will be higher. So Nagoya University is constructing the automatic production line, which will work with a speed of about more than 10 meters per day, 10 square meters. And it will be ready for production test in September. Also, we prepare new target mover, which will be able to operate with a large module of the size up to 40 by 40 centimeters. The large volume of models will allow us to speed up scanning. And during exposure, we use intensity driving control, which give a smooth proton distribution in the model with respect to the constant speed movement. So we are going to keep like this. And after emulsion exposed and developed, the analysis goes into steps. So first step is a fast full area scanning. After this, we are able to reconstruct track segments in emulsion plate and the tracks in the volume, and able to select decays with a angle more than 20 milliradians. So of course, this means at this step, we have just a pre-selection. We select double charm events and our signal events, but we cannot distinguish DS from tau at this step, just to see the tau decay. Well, for this task, we used Hypertrack selector in Nagoya with a scanning speed of 0.5 square meters per hour per layer and resolution of about 2 milliradians. And since we already finished full area scanning for pilot run, but since in the physics run, the amount of emulsion will be higher, to be able to finish each scan of each physics run in 1 year, the new system is under construction, which will be 5 times faster. And on the second step, we will work with the events pre-selected in first step, and we will use a nano-precision system with an angular resolution of about 0.3 milliradian. And on this step, already it's possible to distinguish DS from tau and to register signal finally. So I will, for pilot run, we are working now on the first step, and I will concentrate on this only. The track density level in our models is about 10 to 5, 10 to 6 tracks per square centimeters. Here on the plot, you can see the amount of track and the piece of data. And Anyway, the unique spatial resolution of emulsion allow us to efficiently recognize tracks and vertices. The track finding efficiency in a single film is more than 94%. And here is example how the vertices looks like in tungsten target. And here is a multiplicity of proton interactions in different materials of our detector. Now we are working on comparison of some distributions with those obtained from different generators. And here from distribution of vertices along the model, you clearly can see the structure of model. And the final task at the first step is a search for double charm event topology. You can see here on the picture, we look for charged one-prong decay, and in the same vertex, it should be another charged or neutral decay. Here is shown in neutral, for example. So far, we analyzed just a part of the pilot run data, which correspond to about 3.4 times 10 to 7 protons. And number of registered proton interactions and found double decay topology is in agreement with those expected from the Monte Carlo simulation. Also, flight length distribution shows that our charm analysis chain works. And to conclude, I would like to say that our experiment was proposed to CERN SPS, and it was approved as NA65 about a year ago. So the aim is detection of 1000 DS2 tau decays in 400 GeV proton interactions using emulsion detector with a spatial resolution of 50 nanometers, which will allow to reduce the systematic uncertainty in the new tau cross-section measurement from 50% to 10, and also will allow to study charm particle production. So we successfully performed a pilot run and collected about 10% of the data, performed fast full area scanning, and now we are working on the analysis of this collected data. And also we are preparing to the physics run, which take place next 2 years. So we're optimizing detector geometry and preparing fast emulsion production line and faster readout. Okay, thank you for attention.
Thank you very much. Are there any questions? If so, please raise your hand. I don't see any questions. Maybe I can ask a quick one myself. Just a very simple question. The scanning technology, is it building on the Opera technology, or is it really a new development?
Of course, yes, there are many people which participate in Donut, Opera, and so on. Yes, and Nagoya University participated in Opera, and it's based on this, but now the scanning speed is much more faster. And if you have a look on this new HTS2, which is under preparation, you can see the size, the objective, the table. It's the scanning speed much more improved from Opera times. But yeah, you see the from 72 square centimeters up to 25,000 square centimeters.
I see. Great, thank you very much.
Thank you.
Okay, I don't see any other questions, so I suggest we move on. And now we're moving to a series of talks on neutrino mass. both direct measurements and neutrinos double beta decay. And we're starting with a talk on Katrin from Alexei Lokov. So you can begin. We can see your slides.
Yeah, thank you very much. And I would also like to thank the organizers for the invitation to this conference. It's a great pleasure for me to present Katrin's first results and future prospects here. I would like to start with 3 ways to assess the absolute neutrino mass scale. And the first one is looking at the cosmological observables. In the era of precision cosmology, or we are already in this era, this is a very sensitive way, 100 millielectron volt of the sum of the neutrino masses. This is the value from Planck. The second method is to search for the neutrinoless double beta decay, the process that is allowed if neutrinos are Majorana particles. This is a direct process of lepton number violation, but it is somehow model dependent. And there are several talks in this session, and also Bjorn is going to give some discussion this next week. And finally, one can look at the energy momentum conservation law, and without any further assumption, looking, for example, on time of flight of neutrino from supernovas, or at kinematics of weak processes like tritium beta decay and electron capture on holmium. And it's before Katrin were achieved through the tritium beta decay measurements. Now, why do we use tritium beta decay? The description itself is rather simple. The formula fits on one slide, and it's rather model independent. The neutrino mass enters this rate of the tritium beta decay here, and the general shape of the spectrum is very well recognizable. The neutrino mass, the effective neutrino, only at the very high energetic part of the spectrum near the endpoint. And unfortunately, the amount of events there is rather small. It's 10 spectrum. And tritium was chosen because it has very low endpoint energy and rather short half-life, because it is a super loud decay. But also, as I said, the electron capture on holmium is used in different projects. We need very high energy resolution, low background. And in Katrin, we approach this with the Maki filter technology, but other projects have various techniques to assess neutrino mass as well. Let me quickly introduce you to the Katrin experiment. The Katrin collaboration consists of 150 people from more than 20 institutions, and our 70 meters long setup is located at Karlsruhe Institute of Technology. The setup is split into 6 components: the gaseous tritium source, where the electrons are emitted in the beta decay, and then they are guided by several Tesla magnetic field through the transport section, where the tritium flow is reduced by 14 orders of magnitude. Then the press spectrometer filters out most of the low energy electrons, and the high energy resolution spectroscopy is done with the main spectrometer of Katrin. Then the detector basically counts electrons one by one. And from the opposite side, the beam line is closed with the rear section that has several diagnostic tools on it. The windowless gaseous tritium source of Katrin is a 10-meter long tube where tritium is injected in the center and pumped out at the ends. And the electrons, they are guided with the magnetic field of about 2.5 Tesla towards the spectrometers without any obstacle here. So the requirements for the source, ability of temperature, tritium purity, and tritium pressure. The temperature can also be adjusted in a rather wide range from 30 Kelvin. And of course, the setup has to handle this huge amount of tritium of about 40 grams per day in the nominal operation mode. The high energy resolution of Catherine is achieved through the so-called Markey filter technique, and this stands for magnetic adiabatic collimation combined with electrostatic filtering. The idea here is to guide electrons through the whole beamline adiabatically, so conserving this orbital magnetic moment of electron. And as you can see here, if we reduce or drop the magnetic field by several orders of magnitude, as we do in the center of all the electrons are effectively aligned with the magnetic field lines. And then if we apply retarding potential, electrostatic retarding potential to the spectrometer and to the inner electrode system, we create a high-pass filter for the electrons. Of course, this comes with the cost of having this giant spectrometer that was barely fitting to the streets when transported to the experimental site at Karlsruhe. Now the experimental spectrum of Catherine, the expected rate for each retarding potential that we set is created by a convolution of theoretical beta spectrum with the experimental response of Catherine. And experimental response is essentially computed also from the first principles, but checked through extensive calibration with electron gun and krypton conversion electrons, and Michal is going to give some details in his poster presentation tomorrow. The spectrum is depending on the background rate in this region, the endpoint energy, the normalization of the spectrum, and of course the neutrino mass squared. In 2018, we have performed our first engineering run with very low tritium concentration to check the functionality of all the systems and also to prove the stability of the source parameters under working conditions. And the stability was reached on sub-per-mil level. And this also resulted in a very recent publication of this first spectroscopy of tritium done by Catherine. And in spring last year, we have performed our first science run, 4 weeks long, with very high purity of tritium and high source activity, which was still only 22% of the nominal activity. And we do the scanning in the following way. We change the voltages, go with the voltages up and down, over 2 hours with a 2 hours interval, and we have performed about 300 of such scans of tritium beta decay in this campaign. Then in the analysis, this 300 scans are combined into this nice spectrum of Catherine. Say that here the error bars are enlarged by a factor of 50 just to make them visible. Nonetheless, the fit is very good. The blue line and the residuals are very good. The goodness of fit is excellent. And we have performed bias-free analysis by applying the whole analysis chain first to the Monte Carlo data and only on the final step onto the experimental data. The analysis was done using 2 independent methods of propagating the uncertainties, and both methods agree very well. In our neutrino mass squared best fit result is -1 plus minus essentially 1 EV squared, which is very well compatible with 0. And our endpoint fit, best fit value, can be converted into the Q value of tritium and compared to the independent measurements with the penning traps, which gives also very good agreement. To set an upper limit, we have used 2 procedures, Lockhoff and Kirchhoff, and Feldman and Cousins, and we have chosen this more robust LT method for our first result, which is 1.1 EV at 90% confidence level. Now, let me quickly introduce you to the our very recent results on the sterile neutrino searches with Catherine. We are looking here to a characteristic distortion of the spectrum, kind of a kink coming from the 4th neutrino mass eigenstate. and we're using the same data set as for the neutrino mass. And one of the peculiarities of Katrin is that our signal to background ratio is about factor of 70, which is not so typical for sterile neutrino searches. Here is our result. The blue line is the exclusion curve. Search for the EV scale sterile neutrinos, and in the high mass region we improve a bit on the exclusion of different experiments and exclude some part of the parameter space of the reactor anomaly. And for the low mass range, we improve on mines and troids, limits, and approaching this hint from the neutrino 4. In the future, we plan to probe with our final sensitivity, projected sensitivity, a large fraction of reactor anomaly. A couple of words on the search for key sterile neutrinos. Here we looked into the deep scans far away from the endpoint with our low activity commissioning data, and we found excellent agreement between the data and the model, and sensitivity of about 10 to minus 3 for the mixing of 10 to minus 3. And this will be improved within the Tristan project with novel detector array handling large counts and good energy resolution. One thing that we have to fight with is the background, which is mostly coming from the main spectrometer of Katrin. And among other techniques, we are testing now the so-called shifted analyzing plane configuration, where the volume of the flux tube is effectively reduced, and the volume-dependent background component is reduced as well. We have found that it can lead to improvement of 2 in the signal to background ratio, and we have performed already background calibration and tritium scans in this configuration. In autumn last year, we have performed the second neutrino mass campaign with even a higher source activity than before, and the data will be unblinded soon. And actually on Monday this week, we have finished our third neutrino mass measurement campaign. The analysis is ongoing, and besides, we have performed extensive studies of our source properties and our ways to reduce the background with the shifted analyzing plane. And this brings me to my conclusion. Katrin has the new world-best upper limit on the neutrino mass of 1.1 electron volts at 90% confidence level. And we are taking data to reach our ultimate cell sensitivity of 0.2 EV after 5 years. I have presented the first constraints on the EV scale sterile neutrinos from Katrin, and our first search on the key EV scale sterile neutrinos. We are of course doing some other beyond the standard physics searches as well. And we have just completed our next Katrin run with optimized settings. So you should stay tuned for the new results from Katrin. Thank you very much for your attention.
Thank you very much, Alexei. Are there questions for the speaker? Please raise your hand. I don't think I see any questions. Maybe I can ask a very quick one, Alexei. So when you discussed the Q value determination and you compared it with the penning trap measurements, can you remind me, do you use the penning trap Q value determination as a constraint finally in the extraction of the neutrino mass limit or not?
No, it's we do not constrain it. We just use it as an external comparison of our energy scale knowledge. So this is just a cross-check that gives us more confidence in our energy scale knowledge.
I see. Okay, thank you very much. Okay, if there's no other questions, I suggest we move on. Thanks again. Is the next speaker ready to share their screen?
Yes, I'm ready.
Hi, so Andrea Giacchero is going to talk about new results from the Quarry experiment. Go ahead.
Okay.
Okay, that looks good. We can see your screen.
Okay. Okay. Okay, I would like to thank the organizer to give me the opportunity to present the new result of the core experiment, a experiment currently running at the Grand Sasso and the Grand Laboratories, with the goal to search the neutrino-less double beta decay. In the nuclear double beta decay, two nucleus decay simultaneously, and the two neutrino mode is allowed by the standard model, and it has already been observed in several nuclei, with an expected life greater than 10 to the 18 years. The zero neutrino mode, in which two antineutrinos disappear in a virtual particle exchange, is forbidden by the standard model, but it's allowed by theory behind the standard model with an expected half-life greater than 10 to the 25 years. Its observation would imply the violation of the lepton number conservation, and it would represent a key tool to study the neutrino properties, in particular the neutrino nature, Majorana and Dirac, and the neutrino mass scale ordering, and the CP violation in the lepton sector. The half-life for the neutrino-less double beta decay can be factorized by this formula in red, the first one on the left, where G is the two body phase factor, M is the nuclear matrix element, and F is the new physics term that is responsible for the decay. In case of three neutrino exchange, F is the so-called Majorana mass, defined by the electron entry of the neutrino oscillation mixing matrix. The experimental signature is a monochromatic line at the Q-value of the study decay, and the experimental sensitivity, in case of no peak detected and no zero background, is given by the formula on the bottom of the slide on the left. In particular, the sensitivity is directly proportional to the detection efficiency and to the isotopic abundance of the chosen nucleus, directly proportional to the root square of the lifetime times the detection mass, and inversely proportional to the square root of the energy resolution times the background counts. So to reach a high sensitivity, is important to have a detector with very good resolution, a very large detector mass running for a very long time. The ideal isotope for the study of the neutrino-less double beta decay should have a Q-value greater than the endpoint of the natural gamma/beta background, and less than the starting point of the alpha natural background. This means a range within 3 and 4 MeV. This isotope should also have an high statistic abundance, and the isotope will be available with reasonable cost and procurement time. At last, it should be compatible with the available detection technique, and better if suitable for a configuration in which the isotope is embedded in the detector. Low temperature detectors are powerful tools to study the neutrino-less double beta decay, in this detector, an impinging particle, which releases an amount of energy in the absorber, is detected through a temperature rise that is converted in a detectable signal by a temperature sensor coupled to the absorber. The temperature rise is proportional to the released energy and inversely proportional to the absorber thermal capacity. So to maximize this effect, a small thermal capacity is a mandatory requirement, and this is possible by using dielectric and diamagnetic crystal working at cryogenic temperature. The energy resolution of this kind of detector is only limited by statistical fluctuation, and a relative resolution on the order of per mile are easily achievable. Quore use low temperature detector based of crystal of tellurium dioxide that work both as source and absorber. The decay under study is the decay of the double beta decay of the tellurium 130. This isotope represents a good choice because it has an isotopic abundance of 34.2, and this could avoid the enrichment procedure, and the Q-value is almost above the natural beta alpha background and below the natural alpha background. Moreover, the tellurium dioxide is easy to grow in big crystal with a very low radioactive contamination, and it has a good mechanical properties, and it presents a low heat capacity. As sensor, Quore uses a germanium thermistor doped by thermal neutrons with a resistance that depends logarithmically with the temperature. Quore is the largest thermal detector array ever built. It's composed by 988 tellurium dioxide crystal for a total mass of 742 kilograms, divided on 19 towers, 52 crystal each. Each crystal is a cube 5 centimeter on a side with a mass of 750 grams. The material selection and the assembly procedure followed the stringent radio purity protocol with the goal to achieve a background level in the ROI of 10 to the -2 count per keV per kilogram per year. And the goal with another goal, the second goal to achieve a resolution of 5 keV at the thallium line. In this condition, the expected sensitivity in 5 years is 9 times 10 to the 25 years. That, considering the current nuclear matrix element, this means a sensitivity in the Majorana mass in the range within the 45 and 211 millieV. The base temperature has been reached for the first time in December 2017, and the data taking started immediately after. To cool down this large mass of detector, a custom cryogenic infrastructure is needed. The system has to maintain a cryogenic temperature of the detector, but also all the internal shield. This is very large load, and each cool down lasts around 1 month. The whole structure is designed to minimize the mechanical vibration, and a noise cancellation system has been, an active noise cancellation system has been developed to minimize the vibrational noise to the cryo coolers. From April 2017, 7 datasets have been collected with an average of 900 and 950 valid calorimeter with an average resolution of 7 keV at the Q value. After an initial period discontinued by 2 optimization and maintenance phases, now the data taking is continuing in stable condition, and this was true also during the recent lockdown, and the total acquired exposure of tellurium dioxide is 372.5 kilograms per year. Here I present the result for the neutrino double beta decay. the analysis is based on a Bayesian approach. The likelihood model is composed by a flat continuum with a posited peak for the double beta decay and the peak for the cobalt 60. There is no evidence of double beta decay. The background in the ROI is 0.0138. This is compatible with the target background, and the sensitivity for this exposure is 3.2 times 10 to the 25 years. That means a limit for the neutrino mass in the range within 75 and 350 milli eV. Here, the analysis, the result for the analysis of the neutrino mode, the continuum background is reconstructed considering giant force simulation, the measure detector response, and the experimental coincidence and the detection, the detector self-shielding to constrain local sources. The obtained value is 7.71 times 10 to the 20 years, value that is compatible with the past value obtained with Core 0, with a reduction of a factor 3 on both statistical and systematics uncertainties. So Core now is continuing in running, and the data taking continues, and this stable condition allows to continue data taking with minimal assigned activity also during the recent lockdown. Qualer will reach the target sensitivity in few years, approaching the inverted hierarchy region. The next unblinding is foreseen at 1 ton per year of exposure. In conclusion, the study of frontier subject in neutrino physics required the use of frontier detector. The observation of the neutrino-less double beta decay would prove that neutrinos are Majorana particle. Core accumulated around 400 kilogram per year of exposure, and new data is being acquired. And Core will approach the inverted hierarchy region in few years. The successful performance of Core justifies future development of cryogenic calorimeters, and this is the program of Cupid that is the upgrade of the Core experiment. Thanks for your attention.
Thank you very much, Andrea. We have time for a question, if anyone wants to raise their hand now. Yes. Go ahead, Witold, are you able to?
Yes, Witold Kozanecki, Sarah Sackley. Could you compare your sensitivity in Majorana mass to that of EXO, or rather the new EXO?
In the current sensitivity is less than the EXO sensitivity in this moment, but in 5 years, the goal is to enter the inverted hierarchy region.
Thank you.
Okay, thank you. And a very quick question from me. So just to understand, the next unblinding is expected at 1 ton year, I think you said.
Yeah.
So just to be clear, you mean that the total crystal exposure, not the tellurium-130 exposure?
The exposure of tellurium dioxide, so
yeah,
not of the tellurium-140.
Okay, understood. Okay, thank you. All right, very good. Thanks again, Andrea. And we're ready to go to the next speaker now. Are you ready to share your slides, Davide?
Yes, I'm reading.
Okay, so the next speaker, Davide Chiesa, is going to talk about double beta decay results from Cupid 0. Go ahead.
Thank you. I will present now the results from the Cupid 0 experiments. So I will go fast in the introduction because Andrea, before me, just presented the scientific goal of the neutrinoless double beta decay experiments, and also the feature of the cryogenic calorimeters that will be used in Cupid and that have been used in QP0. I comment the plot that was just shown by Andrea. Here is the sensitivity of quark in terms of the effective neutrino Majorana mass. So you see that quark will approach, or even in the better situation, will touch the upper part of the inverted hierarchy region. And the next generation experiments want to achieve a sensitivity down to 10 millielectron volts. And so to increase the sensitivity, we have to measure half-lives of the order of at least 10 to the 27, 10 to the 28 years. And so we need to have a very large number of observed double beta decay emitters, so a big detector mass of the order of 1 ton, but also isotopic enrichment. And we also need a background close to 1 per year exposure scale. The energy resolution is another key parameter, but as already shown by Andrea, the cryogenic calorimeters have an excellent resolution, and so are a very good option to search for the peak of the signature of the neutrinoless double beta decay at the Q value of the transition. Scintillating cryogenic calorimeters are detectors that, as the cryogenic calorimeters are operated at very low temperature and have high detection efficiency. In addition, they are the crystal absorber is also a scintillator. And so the energy deposited by a single particle interaction is converted into both an heat and a light signal. And by adding a light detector aside near the crystal absorber, we can detect the light, and by plotting the light signal versus the heat signal, we achieve a scatter plot where there are different clusters for different types of particle interacting in the crystal absorber. So we can distinguish beta gamma particle interaction with respect to alpha particles and nuclear recoils that are, of course, a background because we are searching for a double beta decay. Cupid is a next generation experiment. Here there is the link to the pre-CDR document. Cupid means quark upgrade with particle identification. It will be made of 1,500 lithium molybdate scintillating calorimeters enriched to more than 95% in molybdenum 100. The Q value of molybdenum is around 3 MeV. And at this energy, the natural beta gamma background is very, very low. And also we have the possibility to fully reject the alpha background, and an external muon beta will be added to suppress the very low flux surviving inside the cavern of the Gran Sasso laboratories. So by rejecting the alpha background, that is the dominant one in the quark experiment, we aim to achieve a background of the order of 10 to the -4 counts per kilogram per year, with a reduction of a factor 100 with respect to quark background. Cupid has a solid base because it will profit from the quark experience in operating a ton scale cryogenic experiment, and will be hosted in the same quark infrastructure that is running. So quark is running very well. So that's very, very good for the future experiment. In order to go from quark to Cupid, demonstrator experiments have been realized. QP0 is the first demonstrator. There is also QPIDMO running at the Modan laboratories. QP0 is not only a demonstrator for the new technologies to be implemented in QPID, but it is also a competitive neutrino as double beta decay experiment in its own right. So in this talk, I will present the physics results we obtained from the analysis of QP0 data. Here is the picture and the description of the QP0 detector, that is an array of scintillating zinc selenide crystals. So in this case, the double beta decay emitter is not molybdenum, but is selenium-82 that has a Q-value around 3 MeV. And these crystals are enriched to 95% in selenium-82 for a total mass of 10 kilograms of zinc selenide, or 5 kilograms of selenium-82. The crystal is equipped with thermometers and with a germanium wafer cryogenic light detectors at the top and at the bottom of each crystal for particle identification. And there is also a reflecting foil side to enhance the light collection. Here is the timeline of QP0 experiment that started take in 2017. And then it ran for more than 1 year to collect about 10 kilogram per year zinc selenide exposure in the first phase, and with a very good duty cycle. About 74% of time was devoted to collect the data for double beta decay physics searches. After that, there was a detector upgrade, and in the second phase, we collected around 5 kilograms per year exposure. The particle identification in QP0 is performed by analyzing the different shape of the light signals. Here in this plot, you can see how it changes the shape of the tail of the pulse detected by light detector when the interaction is made from an alpha particle or from a beta gamma interaction inside the absorber crystal. And in this way, by defining a shape parameter of the light of the light signal, we can build this scatter plot where we clearly recognize the cluster of alpha events that can be separated from the beta gamma ones above 2 MeV with more than 99.9 discrimination capability. This feature has been applied in the search for the neutrino as double beta decay of selenium-82. In gray here, you can see the spectrum, the heat spectrum, without applying particle identification. And you can see that if we apply the alpha rejection, we significantly reduce the background, and we get the orange histogram. And we can further suppress the background by eliminating the thallium beta gamma events that are in delayed coincidence with the previous alpha decay from bismuth. In this way, we achieve the lowest background ever measured with cryogenic calorimetric experiments of the order of 10 to the minus 3 counts per keV per kilogram per year. And we extracted the best half-life limit on selenium-82. Moreover, we also analyzed not only the region of interest for the neutrino as double beta decay, but we also developed a full background model to describe all the data that have been detected by QP0. In order to understand our background, we divided the experimental data according to different features. One important feature is the multiplicity of the event, and also, of course, the particle type. In this way, by analyzing the gamma lines and the alpha lines that we see in the spectra, we can recognize the sources of background and their position. We can simulate the spectra of each background source with a Monte Carlo Gen4 very detailed model of the experimental setup. And in the end, we perform a Bayesian fit to the experimental data with a linear combination of these Monte Carlo simulated spectra of the background sources. And we obtain the activity of the different background sources. And so we can analyze the different components of our background. Here is the plot for the multiplicity 1 beta gamma experimental spectrum. This is the region of interest where there are the different background components. This is a useful information for the next experiments. And since the 2 neutrino double beta decay shown here is a dominant component in the spectrum, we can perform physics analysis regarding this rate of decay. And also we extracted a limit on CPT violation in this decay. There is a paper here. I don't have time to discuss into the details. Regarding the measurement of the 2 neutrino double beta decay of selenium-82, we got the most precise measurement. It was published on PRL last year. Here is the result, and this is the table of all the possible systematic sources of uncertainty that we analyzed, and we got a final accuracy of the order of 2%. So very, very accurate measurement. Moreover, we also analyzed not only the normalization of this component of the measured spectrum that gives us the activity and so the half-life of the decay, but also the shape of the spectrum. Indeed, there are different nuclear model calculations that involve some approximations, and our experimental data provides a very useful benchmark for such models. And in this paper, we analyzed two different possibilities to describe this decay as a sequence of two virtual beta decays going through only one or more than one intermediate state of the excited state of the intermediate nucleus. And in these two different models, we have two slightly different shape in the 2 neutrino spectrum. We fitted our data with the two models, and we found a strong evidence that the 2 neutrino double beta decay of selenium-82 is single state dominated. Finally, a few words about the phase 2. Since in the background model we found that the muons are the main residual background in QP0, we installed a muon Vito. We also removed the reflecting foil. Here is the tower of the crystals before and after the upgrade. This was done for a better understanding of our background, especially from crystal surfaces. And the removal of reflecting foils allows to measure the multiplicity 2 alpha events. And also a new copper shielding was installed. So summarizing, QP0 is the first double beta decay experiment based on scintillating cryogenic calorimeters and that are also highly enriched. It demonstrated the excellent alpha rejection capability and the lowest background measured with this technique. It allows us to establish the best half-life limit on the 0 neutrino double beta decay and the most precise measurement of the 2 neutrino double beta decay of selenium-82. Just a comment to conclude, Quarry, QP0 and also QPDMO are providing the most stringent limits on the neutrino-less double beta decay and the most precise measurement of the 2 neutrino double beta decay on 3 different isotopes, namely tellurium 130, selenium-82, and molybdenum 100. So this is more than a solid foundation for the QPID experiment. Thanks for your attention. If you have questions.
Thank you very much. Are there questions for the speaker? Please raise your hand or type a question. Okay, maybe I'll just ask a very quick one then, if that's okay. I mean, there are other double beta decay experiments proposing to use molybdenum 100. like Amore. Is there any issue with the supply of enriched molybdenum? How many years worth of enriched molybdenum production does it correspond to for both experiments combined?
Well, yes, the molybdenum 100 is will be produced for Cupid. We have contacts with groups that will produce enough molybdenum 100. Now there is a discussion with the funding agency to cover the cost of the molybdenum 100 enriched isotope.
Okay. All right. Thanks very much. So let's move on. Konstantin, are you ready to share your screen?
Yes, sure. Hello.
Okay, so the next speaker is Konstantin Gustev, and he's going to present very recent results from final results from Gerda phase 2. Go ahead.
Okay. Hello, everyone. So I want to first say thank you to organizers and also for Gerda collaboration to give me such a nice opportunity to present our results here on this important conference. So thank you to the previous speakers. So now you know how important it is to search for neutrinoless double beta decay, so I can skip these slides. And I just want to again mention that the energy resolution is really crucially important for the double beta decay search, since you always have continuous background from 2 neutrino double beta decay process. And another important point is it's very important to reach let's say zero background condition, because in this case we will have the linear increase of sensitivity of the experiment versus exposure. So what is our way to reach such a condition, which we are using germanium 76 isotope to search for neutrinoless double beta decay. Why? First, as has been also mentioned already, that it's important to have as low background experiment as possible, and detector grade germanium is really high purity material, and also this very well known technology and very well established. Another important point about germanium, the germanium detectors, they have a very good energy resolution, actually the best energy resolution amongst all competitors in this field. And in addition, we have our enriched germanium, our germanium detectors enriched in germanium 76, so the efficiency of detection of this decay is quite high. So Gerda used a phased approach. The first phase, where we used detector from the previous experiments, normal coaxial detectors, was finished, and now I'm happy to tell you that the second phase of Gerda also finished in December 2019, and here I am presenting you the last result of our experiment. Here you can see our collaboration, which consists of more than 100 physicists from 16 European institutes. So, and here you see we still keep working in virtuality, in this new reality where all of us now working. So the Gerda cryostat is located in Grand SAS lab, similar in the same hall actually as core experiment. So we have a big water tank instrumented with PMTs, and also on top of the clean room, the plastic scintillator panels. All together, this is our muon veta of our experiment. Here we have a clean room on top of the cryostat. We have a clean room with a lock system and with a glove box where we perform all operations with our detectors. And this is our cryostat with liquid argon inside. And now inside this cryostat, this is a very important part of phase 2. This is liquid argon Vito system, which consists of fiber curtain, which is written out by silicon PMs, and also on top, on the bottom, we have low radioactivity PMTs. Inside this cylinder, we have the heart of our experiment, the germanium detector array, and above, like 40 centimeters above this array, these are our low activity preamplifiers. And so here you can see the picture of one detector. I want to mention that the holder of the detector mainly consists of the silicon, which is also very pure material. This gray plate is a silicon. So some photos which show you the installation procedure and the first immersion of our array inside liquid argon. So phase 2 also it was 2 parts of phase 2. The first part is included 30 enriched BG detectors, 7 enriched coaxial detectors from phase 1, and also 3 natural coaxial detectors. They were 7 strings, which you can see here. And so after 2.5 years of data taken, we decided to try to improve our speed, let's say, of data taken also, and also try to see and improve the liquid argon vector instrumentation. And so instead of natural coaxial detectors, we put 5 recently produced novel inverted coaxial detectors, and also improve liquid argon vector instrumentation. So, and here I also put the goals of phase 2. And so how can we reach our, let's say, background free condition of data taken? For this, we use different techniques of background rejection. So like pulse shape discrimination, anti-coincidence between neighboring detectors, and also starting from phase 2, we have a possibility to read out the light close to the detector from liquid argon. So all of these allowed us to really distinguish between point-like or single-site event, which is neutrinoless double beta decay, and multi-site, and also surface events. And so here also a previous achievement of Gerda. You see that already last year, and it was presented on many conferences, that we have the background index like about 610 to -4 counts per KF kilogram year, which was the best amongst all competitors. And also the limit, the Gerda was the first experiment who overpassed the sensitivity of 10 to 26. So I just want to mention that these 2 goals, like background index and sensitivity, we reached already in 2019. So, and even in 2018. And so in 2018, we decided to perform the upgrade, which I just mentioned. The main goal was to test this novel inverted coaxial detector. You can see one of these detectors here. And also, by this, we increase the mass of germanium and also improve the liquid argon veto instrumentation. And for sure, for the future, for the our successor, for the Langer experiment, it was really important to show the robustness and the reproducibility of the Gerda approach, namely naked germanium detector in liquid argon, which used for cooling down the detector and for active vector at the same time. So here you see the whole phase 2 data taken. So this part, you see here, I put the names of journals where it was published, the results step by step of this part of data taken. Here we made the upgrade, and these are a goal of my talk, the results of my talk. And so I would want to mention the duty cycle of full phase 1, even including this 2-month upgrade period, is close to 90%. If one excludes this upgrade period, since we did not take data during this time, the duty cycle is well above 90%. So finally, we accumulated more than 100 kilogram year exposure. If one includes phase 1, it means it's practically 130 kilogram years of germanium 76, which is biggest exposure ever collected for germanium 76. So now full data set is analyzed. So again, how we check the performance of our system? We do every week the calibration with thorium source. And I'm happy to tell you that the new inverted coaxial detectors perform similarly to BG detectors, but they are at least 3 times more massive. So these detectors are really good candidates and perfect candidates for the future germanium experiments. And also, it's worth to mention here that we really close to the best energy resolution, which was shown yesterday in my runner talk. So we have also similar to 2.5, we have 2.6 kV at Q beta beta. This is also one of the best energy resolution amongst all experiments. Also, the performance of liquid argon beta improved after upgrade. Sorry. So here our spectrum after data quality, muon beta, and INT coincidence cuts applied. You see even here we have something like 10 to minus 2 accounts per keV kilogram year background in the analysis window. And then I want to show you how our pulse shape discrimination works. Here you see how effective pulse shape discrimination removing, for example, alphas from here. You can see, and I would also spectrum from all detectors, but I think it's worth to say that mostly alphas here came from coaxial. For BG and inverted coaxial detectors, the cut, every cut is very effective. And also liquid argon vector works very well. You see here on this plot that after applying liquid argon vector cut, we have practically pure 2 neutrino beta beta spectrum. So, and now when we apply 2 cuts together, one can easily see the great complementarity between these 2 cuts. And after applying these 2 cuts, we reach the background index for all detectors in analysis window 5.2, 10 to minus 4 counts per keV kilogram year, which is the best background index ever achieved. And so now I showed you recently photo of the collaboration when we did recently this remote unblinding. You see, this is just before unblinding, and now we unblind our closed window, close to Q beta beta. Oh, I forget to mention that for sure now all double beta decay experiments are using this blinding approach. So we open the window only after we finalized all the cuts and also finalized our background model. But now you see when we open this blinded window, we found 2 new counts since the last data released here, but I don't want to say fortunately or unfortunately, we still do not have any counts close to Q beta beta. So it means we still do not see neutrinoless double beta decay of germanium 76. So here our statistical analysis, we use 2 approaches, frequencies and Bayesian analysis, and the results are best in the field in both cases. So, but usually people using frequencies analysis, and so here we have a median sensitivity 1.8 10 to 26 years, and the same limit is 1.8 10 to 26 years for neutrinoless double beta decay of germanium 76. So here it's already my last slide. I want to tell you that Gerda successfully finished data taken in December 2019. All our design goals not only reached but even surpassed, as you can see here. Now we have world best median sensitivity and limit, and I think it's really worth to mention that it's proven that in Gerda phase 2 we have linear increase of sensitivity versus exposure, as you can see here. And so we can name again our experiment as the first background-free neutrinoless double beta decay search. And let me say that the success of the GERD experiment really promises us bright future for the next step of germanium-76 double beta decay search, namely LEGEND experiment. Thank you for your attention.
Thank you very much, Konstantin, for this very nice talk. We have time for a question. If anyone wants to ask a question, please raise their hand or type it in the Q&A. Okay, I don't see any questions. Maybe just a really simple one, Konstantin. Are there GERDA analyses still ongoing? Not necessarily, not the neutrinoless double beta decay, but other analyses still in progress? Yeah.
Yes, I would answer yes, for sure. For example, the two neutrino double beta decay analysis, and also the analysis of decay to the excited states, as you know. So yeah, right. Some analysis are still ongoing. So we will provide some new result soon, I would say.
Very good. Thanks again, Konstantin. Okay, so is the next speaker ready to present?
Yes, I am.
Okay, so the next speaker is going to talk about the R2D2 project. It's a great name. A new neutrinoless double beta decay experiment. Go ahead.
Can you see my slide in full screen?
Yes, we can. It looks good.
All right, thank you. Okay, so we'll present the first result that we got for the R2D2 project. I will not describe at all the neutrinoless double beta decay because it's been quite, deeply discussed in the previous talk. But as you've seen, to observe such a rare phenomenon, you actually have some requirements. And the main one are that you need an excellent energy resolution, you need a low background, and you need large mass of isotope. So the question that we ask ourselves is, can we meet all the requirements at the same time? And this is indeed the goal of the R2D2 R&D, which stands for Rare Decays with Radial Detector. So R2D2 is an R&D with the aim of developing a zero background tone scale detector for the search of a neutrinoless double beta decay. And we would like to do it using a spherical high pressure xenon TPC. So the detector, which was proposed by Giomataris a few years ago, is used today by the NUSG collaboration for the search of dark matter. Of course, we have to change a little bit the design because we want to reduce the background in a regime of energy which is different. In our case, is around the Q beta beta of xenon 136, so around 2.458 MeV. On the left-hand side, you see a cartoon that shows how the detector works. So the outer sphere is grounded. And at the center, you have a positive anode, so you have high voltage on it. And all around, you have gas, xenon gas with high pressure. So when a track crosses the detector, it ionizes it, so you produce electron. The electrons are drifted towards the central anode. When you get close to it, you basically enter the avalanche region, so they got multiplied, and you register your signal on the anode. So the detector has many important features. The first one, which is important for us, is the energy resolution. Our goal is to have 1% full width maximum at the xenon 136 Q beta beta. This is what we want to validate, and it's the main goal of the actual phase of the R&D. Is an extremely low background, basically just because of the material budget. So this is reduced to a minimum in order exactly to have as low as background as possible. It's a scalable detector because 1 ton xenon gas is just 1 meter radius sphere at 40 bars. You have low detection threshold, high detection efficiency, and it's a very simple detector. You have only one central readout channel or few of them in an upgraded version. We have today a proto collaboration, so we are approved as a IN2P3 R&D. It started just as a French effort, but lately the Birmingham University from UK joined the effort. And we have established a roadmap. So we have the first step, which is what we call prototype 1. This is what we have today. It's running, it's funded.
It's a prototype that could host up to 10 kilograms of xenon at 40 bars. It's no low radioactivity because we did not care about that at this level. And we want to use this to demonstrate indeed that we can reach the energy resolution that we aim to. If the prototype 1 is successful and we get funded for the following, then we would like to go to prototype 2. This time is a little bit bigger, it's 50 kilograms of xenon detector. And this time would be a low radioactivity detector because with that one, we would like to have the first physics result, and we would like to use it to demonstrate that we can really have zero background. Then of course, if we meet all these requirements and we get funding for the following, we would go to the final experiment, which will be 1 ton background free detector, with which we would like to cover the inverted Masserica region. So as I say, we are now at the prototype 1 phase. So you see a picture of the experimental setup. We were funded in 2018 with, as I say, the main goal to demonstrate that we can reach the energy resolution. So we built a 20 centimeters radius sphere, which is made of aluminum. As I say, this is not low background, but it was cheaper. It was built in the house at CMBG in Bordeaux. And we did not care about being radio pure at this level. We did a lot of efforts to reduce the noise as much as possible. So the detector was placed in isolated and temperature control environment because temperature variation, we found out that would impact basically, in particular, the electronic chain. And of course, they would degrade the energy resolution. We had to take care of vibrational insulation of the supporting of the sphere and of the central anode because the detector was quite sensitive to tiny vibration. And we also work on the development of custom low noise electronics. This was actually done in the frame of the OWEN project, which is a dedicated grant that was actually gained to develop such a low noise electronic. So the setup was commissioned and is currently being operated with argon P2, so 98% of argon, 2% CH4 in Bordeaux with pressure up to 1.1 bar. Now, of course, we would like to do that with xenon high pressure. The point is that even though the sphere was conceived to hold 40 bars, it's not certified for that. And actually, it's quite complicated to certify the existing one. So we will have a new sphere certified for 40 bars in October. And in the meantime, we are completing the xenon recuperation and recirculation system. So this is the reason why the results I'm going to present today are just with the argon P2 up to 1.1 bar. What about detector operation? So to assess the energy resolution and to test our understanding of the detector, we use a 4 becquerel polonium 210 alpha source. So we have an alpha source of 5.3 MeV. The source was deposited on a silver film that is placed on a supporting rod, as you can see in the bottom figure here. And then it's inserted in a hole that was made on purpose at the bottom of the sphere in a way that the source is actually at the radius that correspond to the radius of the sphere, so at 20 centimeters from the anode. We took data with a different pressure, and we used a pulse generator as input in the electronic chain in order to basically to monitor changes of the electronics. So if we had temperature variation, we would actually see that with a pulse, and we could correct for that. We had typically runs quite short, so at level 30 minutes, and we changed the gas after each run. So we did not have to apply any correction due to the gas degradation. Although I'll show you that this is quite understood, it could be corrected offline. We also have a dedicated simulation, which is based on GM4 and Garfield++, and that was used to cross-check the obtained result and confirm our understanding of the detector response in terms of tracks, for example, of its direction, as I will show you in a minute. So the first thing we looked at is detector stability. We took short runs over a period of 14 days without changing the gas. So we wanted to see how the gas degraded in time, because if you have electronegative in your gas, basically you reduce the number of electrons that reach the anode. And this electronegative impurity, they could come from outgassing of material or leakages, and it could increase in time. So you expect to have less electron reaching the anode in time. So you expect to have a reconstructed energy which changes. So on the top plot, you see, for example, the plot that we have for one run. At this level, we did not care about resolution. So it's just the mean of the peak. On the left-hand side at 5.3, you see the alpha source, and higher energy is the generator pulse. And we look at that over 14 days. So you can see the bottom plot. The blue line is the generator, the red line is the source, and the green line is the source corrected. as you can see, we expected generator to be stable, but at the beginning we had actually an increase of its signal. This is because we had an increase of a change in temperature actually that would not allow to take a measurement in stable condition, but you can correct with it. So you can go from the red line to the green line. We found that we have a loss of about 0.05% per hour in terms of the signal because of the outgassing or leakages. And this is something that we can correct offline, or we actually hope to reduce this in a future upgrade of the detector in order to reduce the leakage. Today is at the level of 5 × 10⁻⁹ millibar per second, but we think we could get better than that. In any case, this will not affect the result that I'll show you now, because as I say, we change the gas every time and we had just 30 minutes runs. So, okay, let me spend a little bit of time on this result. These were taken at 200 millibar. So you have alpha tracks with a length which goes between 15 to 20 centimeters. For each event, we reconstruct the waveform, and on the waveform, we can reconstruct variables like the reconstructed charge, so the integral of waveform that we call QT, the width of the waveform that we call DT. And based on different variables that we can reconstruct, we can classify the events. Now, on the plot on the left-hand side, you see the real data that we took. And on the right-hand side, you see what we got with the simulation. So we were quite happy of finding a good agreement between that and simulation. And in addition, the simulation allowed us to really understand the shape of data, because on the left-hand side, so on data, the color code just represents the number of events that you have. Whereas on the right-hand side, the color code represents the direction of the alpha tracks. So black points are alphas that goes directly towards the anode, whereas yellow points are alphas rather orthogonal to the radial direction, so they go against the outer sphere. So what I call region 1, as you can see, these are events for which we do not reconstruct the full charge of the events. This is because actually the alpha tracks end in the outer sphere, so of course it doesn't deposit all the energy inside the gas. And we actually understood also the dependence of the signal width in terms of charge. So for a smaller signal, we found out that because of noise, they would go under threshold sooner. So tracks at very large angle would have a smaller DT, so they would be narrower. Region 2 represent the events that we use for the energy resolution. So the events that deposit all the energy inside the gas. Now, even there, the simulation allows us to really understand what happened, because you would expect that tracks with larger angle would have a smaller DT. Why? Because you would have energy deposit at the same radial distance, so all the electrons would drift and reach the anode together. This is not the case, and we found that the smaller DT comes from tracks that actually go directly towards the anode. And this is because the effect that dominates is not the drift of the electron, but is the diffusion. So when you actually have electron deposited far away, you have a larger diffusion, and this is the reason why the smallest DT is got with tracks that go directly to the central anode. So we're quite happy to really understand the detector response thanks to this detailed simulation. Coming to the resolution results, so we compute a resolution of 200 millibar at 1.1 bar. As I say, at 200 millibar, the tracks, alpha tracks goes between 15 and 20 centimeters, whereas about at 1.1 bar, you have between 3 and 4 centimeters. Now, as you can see, in the two cases, we have roughly the same resolution. So we found 1.2% for with a maximum 1.1 bar and 1.1 at 200 millibar. This is really important for us because we demonstrate that we have no impact on the resolution due to the length of the tracks. And this is important because in neutrinos double beta decay, what you want to reconstruct are electron tracks. So of course, they not point like energy deposit. And we show that this does not spoil the resolution. We estimated at the level of 0.6% the contribution of the source itself and of the electronics tend to test with the generator, which actually gives us an intrinsic resolution of the detector at the level of 1%. Now, what are the next steps? Of course, this is very promising. We're very happy with that. However, what we want to do that is demonstrate that we can have the same energy resolution at high pressure. And as I say, to do that, we need a new detector certified for high pressure that we will have in October. We want to do it with electrons. So we already have a bismuth 207 source. However, in order to contain the electrons inside our sphere, we need at least 10 bars. And then again, we need to go up in pressure. So we will do that as soon as we have the new sphere. In October, we also have the recirculation and recuperation system for xenon, so we can go from argon to xenon. Of course, we do not throw it away after each run as we do with argon. So we really need to make sure that we can recuperate it and recirculate it to purify it. And we want to do it with a diffuse source. We had some ideas, but we still do not have any clean radon source because the test that we did, the source we had introduces electronegative impurities. So we saw a different energy deposit in terms of the radial position, which is not what we want to observe. We will carry on with developments of the electronics, and we did some tests in order to read the scintillation light with a silicon PM. This is really important because at the end, we would actually like to have the T0 to reconstruct the radial position of the deposit. You can see here a screenshot of the oscilloscope. So this is very preliminary. We just got this measurement. In light blue, you see the first peak of scintillation light. In purple, you see the detector signal, which is about 100 microseconds after because you have the drift of the electrons. And you can even see a small bump when you have the detector signal, which is light from the avalanche. We also work on the possibility to use a multi-sensor anode, which is called Aquinos. This would have several central anodes instead of one and would allow to have basically a lower high voltage on the anode to get the same drift field. So these are the main topics we're working on. So I come to my conclusion. So we have now a collaboration which has been established. We are approved by IN2P3 as an R&D. We did some tests. So we computed some sensitivity studies, and we found out that in principle we could have competitive sensitivity with small masses, and potentially we can have a zero background detector with large masses. Of course, this is what we have to demonstrate with this R&D. We have a good detector understanding, so we found a resolution at level of 1.1% with alpha at 5.3 MeV. And we demonstrated that the energy resolution is not degraded going from point-like energy deposit to long particle tracks. Now we have to move on and confirm all these in xenon at high pressure. And of course, depending on the success of this R&D, we really hope to move on and build a prototype that will allow us to do some real physics results. Thank you very much.
Thank you for the interesting talk. Are there questions from any of the attendees? Please raise a hand or type it now. Don't see any questions. Maybe I'll ask just a quick one then. You didn't say so much about the prospects for being zero background. Can you say a few words about that? What's your expectation in terms of single site versus multi-site discrimination and so on?
I didn't talk about that because this is not the goal of prototype one, but we did some sensitivity studies with simulations. So we actually published a paper with the expected sensitivities that we could get with a 50 kilogram detector. Basically, as I say, the low background comes from the fact that the detector is really simple. So you just have a copper sphere. And when we did a simulation, we assumed 10 microbecquerel per kilogram of copper, which is actually conservative since we found on the market copper 10 times better. And with that simulation, we found out that the intrinsic background could actually come from the copper because all the external background could be reduced. In the final setup, we would have liquid scintillator outside in order to reduce that. And of course, some shielding, and you would go underground. So with the simulation that we carried out, we ended up with, I think it was about 2 events per year. But as I say, we were conservative on the estimate on the copper purity that we could have. So then again, this is Gen 4, so we will have to validate step by step. And if we manage to validate the resolution, we will go to a low noise sphere to be operated underground to really demonstrate that we can go zero background.
Okay. Okay, thanks very much.
Thank you.
Okay, is the last speaker ready?
Yes.
Hi, so yep, now we're going to hear about the development of a new self-vetoing structural material that may have application in low background experiments. That's PEN. Okay, so you can start. We can see.
Yes. Okay, so first I want to thank the organizer for this opportunity. I'm presenting on behalf of the PEN working group. I will present the usage of PEN as self-vetoing structural material in low background experiments. So first, let me introduce the PEN consortium. So we are about 25 people working on different aspects of R&D in order to produce low background PEN that could be used as active structural material in low background experiments. And most of the people working on PEN also is part of the Legend collaboration. So what is the motivation for this type of development? So as was presented in all the previous talks, you can see that rare event physics experiments demand a very ultra low background. So to do that, so we need ultra pure materials for the structures and also for the detectors itself. So in general, what happened in some experiments that is you have the detector, but you need some support structures around the detector to place the detector. And if you take, for example, I'm taking just two examples, for example, Core and Legend 200 expectation for the background. So you can see that an important source of background, or the dominant source of background, are the backgrounds coming from the outside. So some backgrounds are produced in the structures, can induce by muons, go through these structural materials. And in addition, if the detectors, for example, are placed, as in the case of Legend, in liquid argon, so there are light that is produced and can be used to veto these external backgrounds, but these support structures can absorb this light that can be used to veto the external background. So we want to go to the next level, to one-ton experiments, so we need to do better. And that's the answer that we want to provide with PEN. Then the idea is replace all these inactive structural materials with some cell-bonded active material, which we think is or can be PEN. So what is PEN? So PEN is a commercially available polyester. So it has a yield strength higher than copper at cryogenic temperatures, which is very good because most of these experiments work at cryogenic temperatures. There was a first evidence in 2011 of fluorescence. In addition, it has wavelength shifting capabilities. It has been deployed, for example, in the protodium dual phase. And all these properties make PEN ideal to use as a structural cell-bonding material. You can look, for example, at this publication here. So the first thing that we need to check is the mechanical properties are okay to replace the structural materials. In most of the case, copper is used because you can achieve a very good radio purity. And we have performed some tests at room and cryogenic temperatures, as you can see here in these photos. And it was found that PEN has a high structural stability at both room and cryogenic temperatures. In addition, PEN is very chemical resistant to most of acids, which is good because it can be aggressively cleaned in order to remove some remaining surface contamination, for example. So now we know that we can replace copper by PEN. So what about the scintillation properties? So PEN scintillates in the blue regime. Here in this plot, you can see the emission spectrum. It peaks above 450 nanometer, which is ideal for most of the photosensors. And it has a light yield of about 1/3 of the standard plastic scintillator, which leads to about a bit more of 3,500 photons per MeV. In addition, as I said before, it can shift the VUV light to visible light, which means that can be used to shift the light from liquid argon or liquid xenon, for example, to visible light to the photosensors. And it can do that with an efficiency of about 40% of TPV, which is the standard material used for this shifting, but with the advantage that producing big surface is much easier in the case of PEN. In addition, we have the possibility to have a PSD, a pull shape discrimination, which is very good because we can do alpha decay identification, for example, to identify surface background, and it has an attenuation length of the order of few centimeters. Here in this example, I'm just showing the light output when we use some PEN samples and we excite with a bismuth source. So this peak corresponds to 1 MeV electrons. It's about 400 keV electrons. And here just to show that we can have a good PSD discrimination when using a Californian source. So we have the scintillation properties. What about how easy is to produce any arbitrary shapes? So we need to take into account that PEN is a semi-crystalline polymer, and the crystallization can lead to the polymer appearing opaque, and we need to avoid that. But PEN must be cooled from about 300 to 200 degrees Celsius in less than 10 seconds in order to remain amorphous and transparent. And this can be done using the injection molding technology. We have done some progress on this matter. We have produced different shapes, plates, containers, capsule fibers, and also there are current efforts to synthesize pen at ORNL. Here you can see some of the arbitrary shapes that we have produced. We have, for example, this type of capsule that you can imagine that you can encapsulate your detectors to protect from the backgrounds coming from the outside, for example. So we have performed some fish production run under clean condition that will be used to produce holders for the Legend 200 experiment. So we're starting from raw material. So you can see here the pellets. Then these pellets were cleaned aggressively. And then some parts were produced in a clean room using the injection molding technology. As you can see here. And here you can see a finished plate. You can see clearly that it is scintillating. And the entire process took less than 4 minutes, which is good in order to avoid exposition of the material to the backgrounds. And we have used this first production to define a protocol for next productions, and a publication is coming soon. So what is the radio purity that we have achieved in this first production run? So we use about 20 kilograms of the pen samples that were produced to measure at 2 underground laboratories at LNGS and Modan. And we have this final result. We have a few tens of microbecquerels per kilogram. And if we take into account that from one of these plates, we can machine several holders, which we expect to have about 5 grams per detector mount base plate, we end up with an activity of less than 1 microbecquerel per plate, which is very good. So as I said, we need to machine these plates in order to produce the holder. We have done this already, a first production. This was done at the Tennessee University Physics workshop. So in order to prevent a possible contamination, we designed a jig in order to minimize the pen plate exposure. As you can see here, the pen plate is placed between 2 acrylic plates, and then the plates are machined. In that way, we minimize the exposure to the any possible source of contamination. All the tools and machines were cleaned. So you have the method that we use. Then once that these plates were produced, I just want to say that the geometry was optimized doing some mechanical simulation in order to minimize the mass. So here you can see the red parts were the parts that were cut, and here you can see a final plate, how it looks like. So first we did some tests at the Tufts University in the cryogenic facility, and then the planes were also transported to LNGS, where were cleaned again and were mounted with in some germanium detectors that are being used for the post-Gerta test at LNGS. So in about 40% of detectors, we have some pen plate, and this will allow for the direct comparison with the silicon plates. As Konstantin said, in Gerda, silicon plates were used to mount the detectors. But we had some preliminary results that show that at least pen is not affecting the response of the detector, and we are analyzing, we're expecting more data that hopefully we can have some preliminary results of how efficiency is pen in this configuration. And now we are making the production for Legend 200, and also continuing with the more R&D for Legend 1000. I just want to thank the people from Legend that they make it deployment possible at the LNGS. Now also we need to characterize the optical properties. To this end, we have mounted several setups consisting of PMTs, where we can place the pen samples and they can decide with a radioactive source. We have some preliminary numbers for LIGL. We now have the emission spectrum. We know that the attenuation is the order of few centimeters and wavelength dependent. and the surface also are being studied. We have developed also a detailed GM4 simulation of the setups, and that will allow us to have an absolute values for light gel, for example, absorption as function of the wavelength, and also to characterize the surface effects. The idea is that we can use then these results as input for detailed studies on optimization of PEN in the context of legend. So this brings me to the summary. So I hope that I have convinced you that PEN is an attractive scintillator that can be used as active structural material. We have performed a successful production of low background pen holders for Legend, which has been optimized for Legend 200. We have defined a protocol for production under clean conditions. And also the first prototypes of these pen holders were deployed at the LNGs during the post-Gerda test. The optical characterization is ongoing. We have some preliminary numbers for light gel attenuation, and also we have developed a detailed GM4 simulation to have a more complete understanding of the effect of PEN in Legend. We are preparing papers now on the first production run and the synthesis, so stay tuned for that. And then our next steps will be the production of enough holders to mount the Legend 200 detectors, and also extract the absolute optical parameters at light gel, attenuation as function of wavelength, and characterize the surface effects, and also study and characterize the wavelength shifting capabilities. Of course, continue with much more R&D for Legend 1000. So that's all. Thanks for your attention. I know there are questions.
Thank you very much. Are there any questions for the speaker? Please raise your hand or type a question. I don't see any questions. Maybe just a very quick one from me. If I understand correctly, you haven't directly measured the radio purity of the pieces after machining. Is that right? You've measured the radio purity of the molded pieces before machining, but not.
Yeah. That's right. So we measured before machining using this protocol. But the idea for Legend 200 is that we will produce the holders with enough anticipation in order to measure before installation in the experiment. But for this post-Gerda test, we didn't have enough time to measure after the machining.
Okay. All right. Thanks very much. Okay, I think we've come to the end of the session now. So I just want to thank all the speakers again for some very interesting presentations. Thanks everyone for listening in. I don't know if the organizers want to say anything. I think there's a poster session immediately following this that people are, of course, invited to attend. Do the organizers want to say anything else?
No, I think no.
Okay, in that case, we end the session, and thank you very much, everybody. Have a nice day. Bye.
Bye.